Good morning, everyone. This is the second day of the webinar. Very soon we are going to start our webinar. So please be with us. Our speaker is really fine. Dr. Gade? Dr. Gade, are you there?
Yes, sir. I'm here. Good morning, sir.
Very good morning. So, I, Dr. Alok Srivastava from Bank of Pious River, Manamda, and second oldest city of India, Bharuch, on the name of Raghu Rishi. I welcoming you in the second day of webinars. Today's session is divided in two sessions. The first half, there will be two lectures, and remaining two at second half. So, I would like to request Mr. Arvind Chaudhary, Assistant Professor Agriculture Studies, SP College of Horticulture and Forestry, to introduce today's speaker and his detail. Over to Dr. Arvind.
Hello, sir. Hello.
Hello.
Sir,
good morning.
Good morning, sir. Sir, please make the co-host to Arvind, sir.
Okay, sir, he's right now. He's not with you.
He's with me, but he working on another system.
Wait. Now he's closed. Please.
Okay.
Our speaker, Dr. Subhash Yadav, is joined now. So I make him as a co-host. Good morning, sir.
Good morning, Subhash, sir.
Good morning, Subhash, sir. Subhash, sir, can you hear me?
Yeah.
Very good morning, sir.
Yeah, I think now it is.
Yeah, it is audible. It is audible now.
Actually, I have joined through two devices, one from mobile and one through my actually desktop, which is not having camera. So actually allow me another one, which is Dr. S.K. Yadav, that is on desktop. Unmute me.
Yeah, sure. Thank you. Now I am leaving that one, first one.
I request Dr. Arvind to introduce today's speaker. Dr. Arvind, over to you.
Yes, sir.
Very good morning to everyone, and welcome all of you on second day of webinar on diagnostic and remedial measure for common errors in application of statistics, organized by Department of Agriculture Statistics, Navsari Agriculture University. I hope that all of you enjoyed yesterday two sessions, and I am sure that today you will also enjoy all our four lectures, because today we have very brilliant and representatives in agriculture statistics, Dr. Subhash Kumar Yadav, sir. Today we have with us Dr. Subhash Kumar Yadav, sir. Presently, he is working as assistant professor at Department of Agriculture Statistics of Baba Saheb Bhimrao Ambedkar University, Lucknow. He has more than 13 years of experience of teaching and associate more than 10 years with research activity. Dr. Yadav has published more than 50 papers and delivered more than 20 invited talks at various occasions. With this, I invite to Dr. Subhash Kumar Yadav, sir, to deliver the lecture on very interesting topic, common errors and their diagnostic and its solution in regression analysis. Dr. Subhash Kumar Yadav, sir, please, I hand over you to sir.
Thank you, Doctor. Very good morning to all of you. First of all, I would like to thank to the organizers, especially Dr. Alok Srivastava, sir, to invite me and to give me the opportunity to express my view regarding the regression or some kind of pressure to deliver this, and actually not delivering, just we are just this, we will be discussing, we will be sharing our knowledge, our what we have gained till I think 13 years of journey. So we'll be discussing what are the common errors in regression analysis and what they are having impact on the estimates of the regression parameters, and what should be the remedy for, if such type of errors are there in the model. So I think without delaying, we should start. Let me, yes, you have allowed me to share my screen. So I'm just sharing that one, and very soon we'll be starting. So definitely it is a pleasure for us that we are celebrating, International Statistics Day on the second day of this workshop. I am sharing my view regarding the errors in regression analysis. So why it is not opening actually? Yeah, I think this is visible to all of you.
Yes, sir, it is visible.
Okay. So now we'll be starting. Yeah. So today we will be discussing the common errors and their diagnostic, and definitely their solution in regression analysis. So we know that regression is nothing but it is one step ahead towards the correlation, where in correlation we actually study the association between two or more variables, but we do not talk about the dependency of one another one, or we don't talk about the type of relationship they are bearing, or say which function relationship they are bearing. So in regression analysis, we'll be looking for the functional relationship between two or more variables, and we'll be discussing also which one is going to be dependent and which are independent, and how they bear the relationship between them. So we know that in correlation, they bear a linear relationship between two or more variables. Linear means if we change one variable, there is a constant change in another variable, then they are having a linear relation, non-linear. So in regression analysis, as Professor Galton has said, that this is the average relationship between two or more variables, and we try to find the functional relationship between two or more variables. And the beautiful part of that is that due to which it is widely used in different areas of application, including agricultural statistics as well, that it predicts the things. So the most beautiful part of the regression is the prediction or forecasting. That is why. So we try to find the relationship between two or more variables, and for any variable, once we find the appropriate relationship, then we can predict the dependent for any value of the independent variable. So we know that first we will be discussing, we know that if we are dealing with the model, say y is equal to fx plus u, and the error term. So we know that y is dependent variable and x is independent, we know here. And what we try to establish the relationship between x and y, we have some actual values of y, we have some actual of values of x. Say x is area and y is production. So we have some data that we have different productions for different areas, say 1 acre, 2 acre, 3 acre, and we have the different amount of production of any crop, say. Then what is the actual relationship between area and production? So we'll try to fit the relationship between two variables, if we are dealing with the two variables or more, and we try to find the functional relationship between the two variables, the most appropriate. So the part which we are fitting, that is, if we are establishing just y is equal to fx plus u, then fx will be the deterministic part, which is which is decided by the experimenter, and U is set as random part. Sometimes we say that it is God's will and Fx is one's own will. So now we try to reduce that U, and on the reducing that one, we try to find the difference between that is observed and estimated, that is error, residual, which is known as residual, and that is random part of the model. So we try to find the residual sum of square, and we definitely minimize that one, and we find the estimates of the parameters through using least square method if the model is linear, and otherwise if it is non-linear, so non-linear models, non-linear methods for estimating the parameters, such as nonlinear least square, steepest descent method of three selected point, or say Liebenberg Markov method. These are the estimation methods for estimating the parameters of the nonlinear model. So there are some what I wish to express here, that there are some assumptions regarding this random term, or sometimes it is also known as a disturbance term. So there are certain assumptions that the linear functional form, the function, it should be in the form of linear function. That is why fx must be linear. Linear, we have said that if it is linear, but if it not linear, then we can go with the some non-linear techniques. So linear means if we are changing x by I unit, there is a constant change in y. So x must be fixed. It is known as, suppose that x is fixed, it is not non-random, and independent observations are independent, so that it is mandatory for the regression analysis to, for the statistical test to be valid, and representative sample and proper specification of the model. So this is one of the important thing, this proper specification of the model. If you are not taking, I mean, model very properly, so the error will be very high. So we are just and we'll use all the appropriate independent variables into the model, and sample must be well represented to it, means it should have almost all properties of the population, and definitely the residuals must be normally distributed, and they should be homoscedastic, or we can say that there must be equal variance for the errors for all the different independent variables, or say for all different values of the independent variable. And there should be no multicollinearity. It means there must not be linear relationship among the explanatory or independent variables. If it is so, then it is not good for the estimates. So it is a impurity of the model. So we will detect it and we will eliminate them. So these are the problematic things. If heteroscedasticity is there, if multicollinearity is there, this is not good for the model. Then the OLS estimates will not be at all blue, best linear and biased estimates. And so there must be no autocorrelation. It means the errors, that is that random terms, errors must not be correlated. If it is so, then it is a problem, and we'll look into the problem, we'll detect them, we'll and eliminate them. And definitely this must be followed if there is no outlier. If there is outlier in the model and in the data, and if still we don't want to, I mean, remove that. If outliers are not of importance, then we should eliminate them. And if they are important, we cannot ignore them, we cannot eliminate them. Then we go for the some robust estimation methods. So definitely, I would like to express here there are basically three problems in say dealing with the econometric data, or say with the panel data in economics. So there are three types of problems. One, the problem heterogeneity, that is if there is not equal variances of the errors for all different values of the independent variable. If it is not equal, if all variances are not equal, then this is the problem of heterogeneity, homoscedasticity. So we will tackle this problem, first problem, and if there is multicollinearity is there, this is problem, and if autocorrelation is there. So these are three violations. If they are violated, so there are theories, and we'll be looking for their remedy through. We'll see what are the consequences if these violations are there in the model, and what are the methods of I mean finding them, and then what are the remedies for these problems which are encountered into the model or into the analysis or into the data. So the first one is, I mean, homoscedasticity, that is equal variance. If there is no equal variance, then this is problem, and the estimates will not perform well. So we have to remove this problem. So we'll see how to detect this problem and how to eliminate. And before that, we'll see if this problem is in the data, then what will be its impact or consequences on the estimates of the parameters of the model. So a critical assumption of the classical linear regression model is that the disturbances UI have all the same variations, that is sigma square, for different values of x. When this condition holds, the error terms are homoscedastic, that is having equal variance, which means the errors have the same scatter regardless of the values of the x. It means the errors, if you plot the scatter diagram of the errors, you will see the equal scatteredness of the errors regardless of the values of x, whether it is going to be very high or low. Then the dispersion of I mean errors is going to be same. When the scatter of the errors is different, varying depending on the values of one or more of the independent variables, the error terms are heteroscedastic. It means the variances for different variables, or say different values of one variable, are going to be different. Then this is the problem of heteroscedasticity, and this is a problematic thing. We'll look into the matter to remove it. See, this is model yi is equal to beta 1, or we can say here beta naught plus beta 1 xi plus u, or say here just beta 1 plus beta 2 xi plus ui. So this is nothing but this is random, this is deterministic part, which is one's own will, and this is God's will, or say this is random term. And here this is supposed to be fixed effect, say this is fixed as this is fixed, it is non-random, so this is fixed part, not non-random part, and there is only this one is random part. So we will have some assumptions regarding this. So this definitely this will be random due to this one, because this is constant plus the random term. So homoscedasticity means the variance of this one are expected ui square, because expected ui will be 0. So there are some assumptions that expected ui is equal to 0, and expected ui square is equal to sigma square. This is homoscedasticity. And if expected ui into uj is equal to 0, this is problem of this is not non-autocorrelation. If it is not equal to 0, then it is the problem of autocorrelation. And if more than one, we are dealing with the more than one independent variable, and they are linearly related to each other, then this will be the problem of multicollinearity. So we'll be discussing these three problems. So see here, this is the case of I mean homoscedasticity, or say equal variance. And if equal variances are not, see here, if ui for a different I, it is sigma square. It means all variances are different, are expected ui square is equal to sigma square. Then this is the case of heteroscedasticity, where variances are not equal for different values of x. So one of the assumptions of the classical linear regression is that the variance of ui, the error term or disturbance term, is constant or homoscedastic. Reason are many, including why the presence of outliers. If this is heterogeneous, maybe outliers are there, so definitely the error will be very high, the difference between the observed and estimated value. So it will increase the variance. So the presence of outliers in the data, incorrect functional form of the regression model. If you have taken, suppose that scatter plot is showing that there must be a say second degree parabola, but you are fitting just a line. So misspecification of the model, or incorrect functional form of the regression model, or incorrect transformation of the data. You are just transforming, you are taking log transformation or say exponential, whatever you are to normalize it. Then if it is not I mean, you are not taking correct transformation, then the heteroscedasticity will be there. So mixing observations with different measures of scale, such as mixing high income households with low income households. So definitely this will be a case of heterogeneity. So heteroscedasticity is a systematic pattern in errors where the variances of the errors are not constant. So variances of the errors are not constant, they are not equal. So heteroscedasticity occurs when the variance of the error terms differ across observations or different variables, say independent variables. So heteroscedasticity implies that the variances, that is the dispersion around the expected mean of 0 in for the errors of the residual, because expected E is equal to 0. So of the residuals are not constant, but that they are different for different observations. This causes a problem. If the variances are unequal, then the relative reliability of each observation used in the regression analysis is unequal. The larger the variance, the lower should be the importance, definitely, or weight attached to that observation. So this will be the problem. Larger variance, so lower the weight, and whether it is going to be reality or not, so it will be the case of heterogeneity. This is an example to just demonstrate that heterogeneity. See, suppose 100 students enrolled in a typing class, some of which do not have. They are not having a typing experience. After the first class, where there would be a great deal of dispersion in the number of typing mistakes. Definitely, those who are beginners and those who are some experienced persons, so there will be a very high difference between the two. So after the final class, that definitely it is going to be small and small. The error variance is not constant. It means it is reducing every time. It falls as time increases. So see here, this is the case of homoscedasticity, where the points are equally scattered around this model, say fitting line, consumption and income. And see, this is going to be heterogeneous. See here, this is going to be very high. As X is increasing, this heterogeneity is also going to increase. See, this is the, you can see here, you can have idea of dispersion for different values of X. Or so see here, this is income, these are different values of this Xi, and see here, this is consumption. So this is if income is very low, then consumption is the dispersion in the consumption. See here, this is going to be low. If it is so high, it is going to be high. It is increasing just. So as income is increasing, so consumption is also variation of consumption is also increasing. You can see here, this is going to be high. So this is the case of, see here, every time if you are changing the value of X, the variance is changing. Rather here it is increasing. So this is the case of heterogeneity. This you can see here in the two graphs. This is for one ideal identical distributions for observations I and j. See here identical, and just you are just changing the different values of I and j. So this will be, you can see here, heterogeneity for the two. What are the consequences? Suppose the variances of the errors are not equal, then what will be? So ordinary least square estimators is still linear and unbiased. They are linear and unbiased, but they are not efficient. It means they are having different variance, maybe high, maybe low. So ordinary least square estimates, they are not efficient at all. So usual formula give incorrect standard error for least squares. If you are just using that formula, I mean simple variance you are calculating, so this is not I mean good formula to calculate the standard error for the estimates of the parameter under consideration. Confidence interval and hypothesis test based on usual standard errors are wrong because your F test is not going to be good. Say F or T, whichever you are applying. What are the these are consequences. And moving ahead, whether the standard error, see here, the experience of heteroscedasticity in error terms of an equation violates classical assumption that expected ui square is equal to sigma square. So this is not actually equal to sigma square, this is equal to sigma I square, or we can say this is not equal to sigma square. And the estimate of the equation with OLS has at least 3 consequences. So these 3 consequences will be there if heteroscedasticity is there in the data. OLS estimation still gives unbiased coefficient estimates, but they are no longer blue because they are not going to be efficient. Because they will have different variance and not constant variance. If we still use OLS in the presence of heteroscedasticity, our standard errors could be inappropriate, and hence any inferences we make could be definitely misleading. Whether the standard error calculated using the usual formula are too big or too small will depend upon the form of the heteroscedasticity, whether it is going to be very high or it is just increasing or decreasing, or somewhere it is increasing and decreasing. So definitely it will depend on the form of the heteroscedasticity. In the presence of heteroscedasticity, the variances of OLS estimators are not provided by the usual OLS formulas. Definitely, but if we persist in using the usual OLS formula, the T and F test based on them can be highly misleading, resulting in erroneous conclusion. Definitely, because if standard deviation or say standard error is going to be high, so standard error is used in T and say in F, because it is variance ratio, and this is here that standard error is used to standardize the statistic. So these two will be giving the misleading. So how to detect the heteroscedasticity? So we can have an idea through graphical method as well, and definitely we'll have some method for their remedy. So this is graphical method to detect the heteroscedasticity. If there is no a priori or empirical information about the nature of the heteroscedasticity, if you are not having idea whether it is going to increasing or decreasing or some random pattern, so you should plot, you should use the graphical method. In practice, one can do the regression analysis on the assumption that there is no heteroscedasticity. This will be the actually null hypothesis, and then do an examination of the residual squared. You have to calculate the squares of the residuals, because the sum of squares will be 0. So that is why we calculate the residual sum of squares to see if they exhibit any systematic pattern or not. Although UI square hat, this is for the sample information estimate of that error, are not the same thing as UI square, they can be used as proxies. So we can use this in place of that sigma square, replacing that one, especially if the sample size is sufficiently large. In that case, we can use this as the estimate of that variance. So we can see in practice different type of forms of the heteroscedasticity. You can see here this is going to be homogeneous this is homoscedastic type data, and this is going to be increasing, and this is increasing, and this way this is increasing and then decreasing, and this is increasing this way. So you can see here all things are written here. You can see an examination of the UI square may reveal patterns such as those shown in figure 8. Figure 8a, we see that there is no systematic pattern between two variables, suggesting that perhaps no heteroscedasticity is present in the data. Figure 8b to e, from the here to the last one, however, exhibits definite patterns. For instance, figure 8C suggests a linear relationship, whereas figure 8D, see, this one is going to be nonlinear relationship. 8D and E indicates a quadratic relationship between UI squares and YI. Using such knowledge, informal, we can one may transform the data in such a manner that the transformed data do not exhibit heterogeneity. So if are looking that if we take log transformation, then this can be transformed into the linear. So you can use that transformation, or just it is going to be this way, then you can take the inverse transformation, log transformation, or exponential transformation to make it homoscedastic. So see here. Now these are the some formal methods for remedy for this are detecting these heterogeneity or homoscedasticity in the data. The first one is Park method, Park test. Park test suggests that sigma I square is some function of the explanatory variable x. It is saying that the maximum say variation is coming from this one. So functional form he suggested that was sigma square is nothing but it is sigma square says homoscedastic part into xi to the power beta into this one error term. So or you just take the log transformation, it will be converted into a linear model. Say log sigma square is equal to log sigma and log xi plus this normal 0 and say sigma v square, where vi is the stochastic disturbance term and which is normally distributed with zero mean and say fixed variance. Since sigma I square is generally not known, Park suggests using sigma I square, this which we have talked in previous slide, this one, as a proxy and running the following regression. So you can just replace this by this UI square hat. So we have here log UI cap square UI cap square is equal to log sigma square, this one plus beta and log xi and plus vi, that is alpha plus beta. So this is going to be a constant. So we have replaced just by another constant, say alpha and plus beta log xi plus vi. So this is equation 2, which which is transformed equation, and you can see if beta turns out to be statistically significant. See here, the main thing is that if we are changing x, how y is changed or this part is changed, it is represented by this regression coefficient. So if this turns out to be statistically significant, it would suggest that heteroscedasticity is present in the data. And if it is going to be 0, it means if x is not having impact on sigma square, say, or say x is independent of sigma square, then this will be the case of homoscedasticity. If it turns out to be, means this beta is not going to be 0. This Glaser test is similar to in spirit to that of Park test. After obtaining the residual from first equation through using the ordinary least square method, Glaser suggests regressing the absolute values of ui these on the x variable that is thought to be closely associated with sigma square, where in Park test we have assumed that this is going to be the function of just x, and in Glaser test we are just saying that this is having some specific function, say the spirit is same, very close relation to that one. So in this experiments, Glaser used the following functional forms where vi is an error term is that will be known as it may be first order autoregressive term. So see here, this is going to be related with this form with the x, with this form with the x, with this form. So there are different transformation of x. You can see here, this is linear and this is say square root, and this is inverse and inverse square root, and this is square root. In this way there are so many methods where you can detect that one heteroscedasticity. So what are the conclusion we will see? in if the data is I mean heteroscedastic. So one of the assumption of OLS regression is that error terms have a constant variance across all values of independent variable x. So if independent say x here independent variables with heteroscedasticity, this error term variance is not constant. And it is not so. So we try to make them I mean homoscedastic through different linear transformation, and we know that the impact is through the independent variable. So we try to find the appropriate relationship between the error and the independent variable, which we have seen in whether in case of Glaser test or in case of say Park test. So more common in cross-sectional data than time series data. So one very interesting thing I would like to hear, discuss. There are three types of data: time series data, cross-sectional data, and the panel data, which is the combination of the two. So time series data means the data on one variable at different time points is time series data. And if we have more than one variables and we are having the data on a single time point, then this is a cross-sectional data. And if we are having various variables and we are having data on various time points, so this is the case of panel data. So in this, problem of heteroscedasticity is more common in cross-sectional data, while autocorrelation is very common in time series data. So even if the heteroscedasticity is present or suspected in the data, whatever conclusions we draw or inferences we make may be very misleading. So this is very important to detect it and eliminate this from the data. Now coming to the multicollinearity, as we have discussed, multicollinearity is a problem where independent variables included in the model, if they are showing some linear relationship among them. So this will be the case of multicollinearity, and this is one of the problem. So the estimates will not going to be very good. So we'll try to find it and detect it and eliminate it. And definitely there should be some remedy to get the best estimates of the parameters of the model. So when two or more independent variables in the in a regression model are highly correlated to each other, it is difficult to determine if each of these variables individually have an effect on y. So it is very hard to get the individual impact, individual contribution of the independent variable to the dependent variable when two variables are very highly associated, independent variable are highly associated with each other. And to quantify the magnitude of that effect, definitely what are their independent contributions. So intuitively, for example, if all farms in a sample that use a lot of fertilizer also apply large amounts of pesticides and vice versa, it would be hard to tell if the observed increase in the yield is due to higher fertilizer or to higher pesticide used. So this is very difficult because pesticide and say fertilizers, manures are going to increase the production of the any crop, yield of any crop. So both are enhancing the production. So it is very so they are having very close relation. They are linearly related to each other. So it is very hard to get the separate impact of the fertilizer as well as of the pesticide on the increase of the production or yield of any crop. So in economics, when interest and inflation rates are used as independent variables, it is often hard to quantify their individual effects on the dependent variable because they are highly correlated to each other. Sir, I would like to know whether there is echo in the problem. Otherwise,
No, it is okay, sir. It is okay, sir. It is audible and it's clear audible, sir.
Okay. Then
Please go ahead, sir.
otherwise, I can switch off one of my mobile and then I can carry on this.
No, it is working, sir. Please.
Okay. Thank you, sir. So this will be the case. How to, get the individual impact of the independent variable, individual contribution of the independent variable on the dependent variable. So this will be the case of multicollinearity. So mathematically, this occurs because everything else being constant. Because we are just considering everything else as constant and we are just allowing their contribution. So the standard error associated to a given OLS parameter estimate will be higher if the corresponding independent variable is more highly correlated to the other independent variables in the model. So the estimate variance, that is standard error of the estimates, is going to be very high, and this is not going to be very good for the regarding the reliability of that estimate, because it is showing very high standard error. So this potential problem is known as multicollinearity. It could be the reason why independent variables that are believed to be key in determining the value of a given dependent variable do not result statistically significant when conducting the basic test of hypothesis, as they are having very high association. So it is very, hard to get the independent contribution because they are having. So what is the B1, say value of B1 and B2 when this X1 and X2 are very highly correlated to each other. So it is very, we cannot say that this is solely impact of B1 is showing the impact of X1 and B2 is showing the impact of X2. So it is not a mistake in the model specification. This is not mistake actually, model specification, but we will see. There must be some common variables, say. So we'll this that is why for the remedy we reduce the dimensions and we collect the closely related variables, and then we make another variable to see its independent contribution. But due to the nature of the data and at hand, because this is not model misspecification, but since they are highly correlated to each other, so the variation in the estimates of the standard deviation is so in the model. It is more common in time series data models because time often affects the values taken by many of the independent variables in these type of models, causing them to be highly correlated to each other. Now we'll be discussing the two types of multicollinearity. One is perfect multicollinearity and another one is imperfect multicollinearity. So perfect multicollinearity is nothing but it is that if there is a perfect linear relationship among the variables. It means if any variable is any one of the independent variable is having perfect linear relationship among rest of the independent variable, then this will be the case of perfect multicollinearity. But perfect multicollinearity occurs when there is a perfect linear correlation between two or more independent variables. That is when an independent variable is actually a linear function of one or more of the others independent variables. When including total annual rainfall as well as rainfall during each of the seasons as independent variables in an time series model. So this will be the case of because it is contributing in total as well, and independently they are contributing some. So this will be the case of multicollinearity when independent variable takes a constant value in all the observations. If they are constant in all, so they are having 100% correlation they are having. If there is perfect multicollinearity, the OLS method cannot produce parameter estimates. So this will be the problem. So this will be the OLS estimates will not be going to be very reliable. They will not produce estimates. All cases of perfect multicollinearity are the result of making a mistake when specifying the model and can be easily corrected by properly specifying the models. And that is why we try to I mean there are so many methods, so backward selection, forward selection, backward elimination, or stepwise regression, so that we select the I mean appropriate independent variables in the model. And severe multicollinearity, a certain degree of correlation, multicollinearity between the independent variables is normal and expected in most of the cases. So multicollinearity is considered severe and become a problem when this correlation is high and interferes with the estimation of the model parameters at the desired level of statistical certainty. What are the symptoms of multicollinearity? The following, when taken together, are considered symptoms of a multicollinearity problem. Independent variables considered critical in explaining the model's dependent variable are not statistically significant according to the test. It means they are not having their independent own they are not showing their independent contribution. And very high R square, high significant F test, but few are no statistically significant T tests. So parameter estimates drastically change values if they are drastically changing values and become statistically significant when excluding some independent variables from the regression. If you are considering all the independent variable and just you are eliminating one by one and the estimates are drastically changing, so this will be the case of multicollinearity. How to assess this multicollinearity? Two methods for assessing multicollinearity in this course: correlation matrix and variance inflation factor. So we can, if there is high correlation, so through this correlation matrix, we can see which independent variables are going to showing very high correlation. So we'll work on that and we'll see. And there are two more methods. One is associated with this one, I mean variance inflation factor, which is also known as tolerance. And one very important and well-known method is method of principal component analysis, PCA, principal component analysis, which reduces, which is also known as dimension reduction method, which is which is used in the factor analysis. Which is also one of the remedy for I mean very important remedy for this problem of multicollinearity. So this is example you can see here. This is I mean the first one, and this third one variable is showing I mean this 63% of the similarity, and this is 73%. You can say 68%. There are, you can see very high correlation. They are highly correlated independent variables. So there is case if the collinearity is going to be high means if it is going up to 0.5, then this will be the problem of multicollinearity. Disadvantages of correlation matrix. Correlation matrix only work with two variables at a time. This we can only see pairwise relationships. If a more complicated relationship exists, the correlation matrix would not find it. If we have more than say very high independent variables. So, and what is the advantage? Working with two variables at a time is simplest and most interpretable. If you see a high correlation, you can make a simple scatter plot. Then you just plot and see of the two variables and see their relationship. You can see whether they are going to be linear, they are going to be non-linear. You can just plot a scatter plot and you can have idea of the multicollinearity from the plot. And this is VIF, and VIF is nothing but it is I mean reciprocal of the tolerance, and tolerance is nothing but it is 1 minus R square. 1 minus R square is tolerance, and 1 upon 1 minus R square is this VIF, variance inflation factor. So variance inflation factor measures the relationship of all the variables simultaneously. Thus, they avoid the two at a time. So you can simultaneously you can have an idea of multicollinearity. Advantages, disadvantages of correlation matrix, because correlation matrix is restricted with using two independent variables at a time. So there is a VIF for each variable. So VIF is based on regressing each variable on the remaining variables. If the remaining variables can predict the variable of interest, then that variable has a high VIF. It means if any variable is having a linear relationship with other variables, then definitely this will be predicted by the rest of the variables. So the value of the VIF will be very high. Detecting multicollinearity, a simple test for multicollinearity is to conduct artificial regressions between each independent variable as the dependent variables and the remaining independent variable, what VIF does. You just take one independent variable and rest of the independent variable as independent, and the one independent variable as dependent variable, and you just calculate the value of VIF for all the variables. So in most of the softwares do it. So variance inflation factors VIF are calculated as, this is 1 minus RJ square, and this is coefficient of determination, this is R square. The artificial regression with the jth independent variable as the dependent. So here if it is this J is showing that this we have taken the xj as the dependent variable and rest as independent variable. So each variable has its own VIF. Ideally VIF are 1, indicating the variable provides completely independent information. See here, this is its unique contribution. In practice, all VIFs are greater than 1. There is typically some degree of multicollinearity. VIFs are considered bad if they exceed 10. So in most of the, statistical analysis, VIF till 10 is allowed, and the analysis is allowed to with that low degree of multicollinearity. And if VIF is going to be more than 10 for any variable, then this is problematic, and then we see the problem. So this is the problem for the this VIF. The variance inflation factor for our example are all quite moderate. The largest one is 3.58. So this is very low in comparison to 10. So we'll go with the collinearity will not going to be serious. So we'll go with the analysis with that of degree of multicollinearity. So this is another example. You can see, suppose interest, instead of ankle diameter, waist girth, and forearm girth, and height, we choose chest girth, shoulder girth, waist girth, and bicep girth, all upper body measurement which we might expect to be more strongly associated with each other, because they are associated with each other. So we can have the problem of multicollinearity is there. So check multicollinearity measures. If there are problem, that is VIF is going to be high, then you must start removing or combining variables before you can trust the tends to be a substantive, not a statistical task. So you have to see the different, all the time you are just removing and you see VIF, then you go ahead. The variables with the highest VIF can be first targeted for deletion if that makes sense. They are the most redundant. So after you do anything, remember to check the residuals gain. What is the now it means whether this residual sum of square or error sum of square is reduced or not. Now suppose you have descent residuals and collinearity measures. Look at the FP value. This is, if this is not significant, stop, otherwise continue to the next slide. It means then you just go ahead and eliminate, or you just add variables. So model selection refers to, see here backward, there are three types of, model specification: backward selection, backward deletion or elimination, and forward selection, yeah, forward addition, and backward deletion or elimination, and the stepwise regression. So in forward backward elimination, backward selection, we use all the variables in the model and we try to eliminate one by one, having very high say correlation or having very high VIF, and we see the value of R square as well as of S square, the residual sum of square. And in forward selection, we just add one by one and see the value of R square and adjusted R square where it is going to be constant, adjusted R square. And in this stepwise regression, both backward and forward type of methods are used. So you can see here. So this is example for backward selection method. You can see examples. You just eliminate one by one, looking into the value of say VIF. And now we come to the last type of error, which is known as say autocorrelation. Autocorrelation means errors are associated with each other. Means previous value is associated with the current value or say next value. The linear regression model assumes that the disturbance term is not autocorrelated. That is expected UI, UJ, or say UT and US is equal to 0 for T is not equal to S. If disturbance terms is autocorrelated, OLS estimators no longer blue. The OLS producers procedure becomes inappropriate in such case. So example of autocorrelation is this: UT is equal to function of these lagged values, and this is, we are just taking first order autoregressive model. So reactions for autocorrelation: incorrect functional form if you have taken, non-linear model estimated by linear model, you have just estimated the parameters through OLS for the non-linear model, and omission of the explanatory variable, variation in the dependent variables will not be explained by the model. Variation in the dependent variables will not be explained by the model. It will show up in the residual differently. Variation will not show in residual, in not a dependent variable. If there is variation in say mesh specification, or I have already discussed that the random term is only U, and due to that there is variation in Y. So this will include autocorrelation, in the variables, and hence often in the error terms. It is the problem of inertia as well. It is a common feature of many economic time series, meaning that they are slow to change rather than being highly volatile or irregular. That is due to the momentum of business cycles. Except the business shocks or say natural disasters there. So these are the implications of autocorrelation. The estimators remain unbiased and consistent. Expected U is equal to 0 ensures the unbiasedness of the estimator. The estimator will be inefficient in the sense that we will be able to obtain estimators with lower variance. False inferences about the significance of the parameters. The usual OLS formula for calculating the variance of the estimators are incorrect, and variance of the estimators will be underestimated. And this is very crucial problem and dangerous, that your estimates variance will be underestimated. So large T statistic and variables which are not important, insignificant, may be considered as significant in this case. So this will be the very misleading. And how to detect? By graphical method: plot residual against time, scatter plot of residual against lagged residuals. You can apply run test, and one of the important which is used by many of the experimenters, which is Durbin-Watson test. And the ratio of the sum of square differences in successive residuals to the RSS measures only the presence of the first order correlation and assumes that lag of dependent variables is not included. If you are just, taking the model without that lag value of the dependent variable, it means you are just including the independent variable in that. No autocorrelation is its null hypothesis, in its null hypothesis. So, but D has no unique critical value, this Durbin-Watson statistic. So sample size and the number of regressors are used to calculate upper DU, that is upper bound of this Durbin-Watson statistic, and lower bound of this Durbin-Watson, to determine the rejection regime, where to accept, where to reject, and where to continue the sampling, say. The rule of thumb is that if D is equivalent to 2, 1 minus rho, D is equal to 0 if rho equal to 1, and D is equal to 2 if rho is equal to 0, and D is equal to 4 if rho is equal to -1. These will be three type of extreme values case. So reject the null hypothesis if D is less than DL, accept the null hypothesis if D is greater than DU, and inconclusive region if D lies between DL and DU. So these are some, technical terms, mathematical formulas through which you can detect autocorrelation, box jump Q statistic, autocorrelation coefficient of kth order, and you can gamma k, which is covariance between ET and ET minus k, and this is gamma naught is nothing but it is variance of ET at that time, and this is the ratio of the two, and individual hypothesis that rho k is equal to 0. So this way you can calculate. There are so many, you can calculate partial correlation coefficient as well, and so this is the diagram of the Durbin-Watson test, where we can take decision in between no decision, as we have discussed, in between no decision, and if here this is a negative correlation, this is positive correlation, and this is the case of no autocorrelation if it is lying between du and 4 minus du. You can see here the case. These are different values you can see for different values of k. And this is the output in spaces. You can see the value is Durbin-Watson statistic value is this first order autocorrelation problem, and you can see here this is very close to 2, but it is very far from that one. So this is the case of autocorrelation. You can see for the data time series data, a systematic pattern you can see in residuals. This is the you can see here the autocorrelation and partial autocorrelation, and you can plot the graph between the two, and this way you can see the pattern in that, and you can check the first and second order autocorrelation problem whether detected or not. So correcting autocorrelation, if the results of the Durbin-Watson test indicate the presence of autocorrelation, then OLS does not provide the best estimates of the model's coefficient. The alternative approach is to use what is known as generalized least square. GLS is used to get over the problem of this autocorrelation. One variation of the GLS approach was the method of weighted least squares used to correct the problem of heteroscedasticity, if you remember that one. So you can correct this way. We are using the lagged value of that. This is a first order autoregressive model. So at that place you will use that one, and this way you can calculate the model. If we could get rid of the term this rho into this, the multiplicative term, then from the above model, we could use OLS to estimate the coefficient. Then you can, if you are just if this is not having very contribution and you can ignore, then that we can use the OLS term. To do this, we multiply the initial model to rho and take the 1 period lag of that model, say this one, and use that in the model, and then use the OLS to estimate the parameters. And this will be the transformed model, and you can then you apply the OLS. So this equation is known as generalized linear model, and then you can apply that method to estimate the parameter OLS. So the generalized model could be estimated by OLS if we knew the value of rho, this autocorrelation. One way to estimate the generalized model is the Cochrane-Arcout method. This is one of the very famous method for the remedy of this autocorrelation. that eliminates the problem of serial correlation. This, I mean, autocorrelation is also known as serial correlation. The Cochrane-Orkut method first obtain the estimate of rho. This because GLS is applied there. If this rho is known, and if it is unknown, then we first get its estimate and use that. So Cochrane-Orkut method use that, it estimate that one, and then use the OLS method in GLS. Then in generalized model we use the OLS method. The Cochrane-Orkut method could be general be used instead of OLS when autocorrelation is present in a regression model. So you can, if autocorrelation is there, then you should apply Cochrane-Orkut method, which first estimate this rho. You can see here, this is going to be at the second order. This is 2.2, so this is very close to 2. I mean, the autocorrelation problem is corrected there. See here. These are some references which had been used from where I have borrowed these slides, and if you have any query, any question, I will be pleased to answer that one. So please, sir.
Thank you, Dr. Yadav sir, for such an impressive presentation. Dear participants, you just listen reputed scientist Dr. Yadav sir. He discussed very well about the common error associated with regression analysis like multicollinearity, autocorrelation, and heteroscedasticity, and also he mentioned the how we remove this error. So I don't think anybody have a doubt, because sir present it very well. But still anybody have a doubt, then you can ask the question in the chat box.
So thank you, sir. Please share it in my email. I think you are just showing this certificate.
Thank you, sir. On behalf of our organization team and Navsari Agriculture University, as a take a vote of thanks, I am presenting this certificate to you.
Thank
we
you.
are thankful to you, sir.
Thank you. Thank you. Most welcome.
Thank you,
Yadav sir. Once again, thank you. I know this topic is somewhat, from very college days. I am expecting somewhat, with more illustrative examples should be there to make in this particular topic, especially econometrics, more interesting. And in fact, that wish now somewhat up to some extent is fulfilled. Thank you, sir.
Definitely. I was given, sir, only 1 hour, and the topic was errors. So I tried to discuss all types of error in the model. If otherwise the 1 hour is sufficient to discuss only one error.
I do agree, sir, because this topic is required. In fact, 2 or 3 subjects together makes one.
Definitely, sir. Definitely.
So I understand what kind of difficulty is there, how up to which extent we have to put example, and up to which step we have to stop. Thank you, sir, and so nice of you for giving opportunity.
Thank you, sir. Thank you, sir. Thank you. Thank you. Most welcome, sir. Thank you, sir. Thank you. Okay, sir.
Participant, our next speaker is Dr. Kingsley is joined. So I request Dr. Arvind to introduce him. Please, sir.
Okay, thank you, sir. So now we have with us renowned speaker Dr. Kingsley sir. He is working as scientist specialized in agriculture economics at an iShare organization at National Institute of Agricultural Economics and Policy Research at New Delhi. Dr. Kingsley sir has a good experience of teaching and research experience. His core strength lies in application of econometrics techniques, mathematical programming, and handling software like R, SAS, and GAMS. With this, I invite to Dr. Kingsley sir to deliver the lecture on common error in application of econometrics and linear programming, a partial alternative. Please, sir, over to you, sir. Dr. Kingsley sir. Sir, please unmute. Kingsley sir.
Yeah, am I audible now?
Okay. Yes, sir.
You're audible now, sir. Please.
Yeah, thank you. Thanks for giving me opportunity, but you have not told me who is the audience so that I can relate with them. So who are the target audience?
The targeted
Are they
audience.
students? Are they faculty?
Okay, I'm explaining you, sir. Basically, target audience is somewhat different. Basically, most of the students having doctorate or postgraduate student, and different faculty is also there, and more or some data scientists also joined this webinar. So I know this is somewhat difficult for us to explain.
Okay.
I know.
Okay, sir.
Okay, sir. Thank you.
Yes, sir. So my voice is audible. I also. So if any problem, you just let me know. Okay.
Yes, you're audible clearly.
Yes, sir. So I was presenting. Maybe this topic should be like this: diagnostic and remedial measures for common errors in application of statistics in maybe social science. So because I'm not purely working in statistics. We are working in economics and extension. Those who, whatever their problem, like adoption studies, or it is something like econometrics, like modeling demand and supply estimation. So this is what our major work. So I will try to relate. So how, what is the problem I have faced, and what are the issues we could solve. So this is what my major focus is. Okay. So it is not simply remedial measures for common error, meaning not like diagnosing errors. I think probably someone might have already handled that. So let me start with the econometric modeling. So first it starts with economic theory. I think by the way,
it is very difficult.
Okay.
You know.
Okay. Because I want to relate, that's the reason I just asked. Because it is pure statistics, maybe they may be dealing with sampling or designs of experiments or forecasting. I am somewhere related to, no, it is something forecasting or econometrics. That's just I want to.
More or less, you can take with the help of suitable example, you can explain. Please.
Okay, sir. Okay. So since our domain is economics, so we often apply econometric models. So there are mathematical models are there, like linear programming and non-linear programming. There are so many models are there, but especially when you want to study the policy questions, mostly people use these econometric methods. So how we start with that? It is first we start with economic theory. I think probably you might have heard production function. Just you, if you might have studied even introduction to microeconomics. So it says that if you apply more input, your production function will go up for some direction. Some input, it naturally comes down. It is a negative marginal productivity, you can call it. So the theory only tells us it's a general idea. Then already we have mathematical models are there. Like example, if you want to estimate economics, simply a geographic representation of a input output relationship, just like a curve. But in mathematical model, it tells us what are the variables to be added. Like it is what are the independent variables. It may be fixed variable like fertilizer, it may be like a seeds. So like that, what are the inputs should be added? That's how the mathematical model says. If I take one more example, like we have used profit function. They arrive, even the cost function, there's a relationship between production function. Production function is nothing but is a technical relationship or it's a physical relationship between quantity of output and quantity of input. Okay, it is something like you can experimentation. When you conduct experiments, what you do, fertilizer in different quantity. Then you see what is output response. That is something like a production function. Similarly, you can find out the irrigation response. You can find out the yield response. There are so many responses are there. But I told you that in the production function is a physical relationship between output and input. So in the mathematical theory, what it gives that this production function has some relation with the cost function. So what I'm saying that they have a mathematical model. It is simply it's an economic theory. It is a mathematical model also there. Like a profit is a function of prices of output and prices of inputs. Cost is a function of quantity of output and price of input. So the mathematical model, what variable you should include, that kind of suggestion gives. So once you have the economic theory, the broad principles, and the mathematical model, what are the variables should be included or what specific should be included, then we come to the econometric models. And you think you cannot do it. So econometric has some relationship, like if you want to find out the wage. So wage function always something it should be related with the output price and experience and education, something it gives some idea. So we that's how we come to an econometric model. So before going to the econometric model, you should have some basic idea. It's something like a statistics only, but what we add here, that economic theory plus mathematical model of economics, what you say is that then we combine that in economic model. So like if I want to estimate national estimated consumption function, like in national level, we want to see that what is the proportion that my consumption will increase. Example, if you take this, maybe 5 years back, the cereal consumption was, the per capita cereal consumption was very high, and relatively high. But over the year, our per capita income has increased. So people now diversified their consumption. So what they did, now they diversified, maybe they are consuming more food, they consume more non-veg food. So the cereal, per capita consumption of cereal is keep declining. So it is gives some idea. That's what I'm saying. If I want to put a consumption function, the econometric theory arrive ideas from economic theory and mathematical model. So once you got idea, if you want to estimate this, these are all very once you estimate this consumption model. So it says that margin propensity consumption. Maybe you see some coefficient. Maybe usually it is 0 to 1. It should be greater than it is positive 1. So greater the margin propensity consumption, it's more. That means whatever the income comes, you are large amount of income you are consuming. That is good for a country. It may not be good for an individual. Like if we have a theory like business theory, if you are saving a lot of your income, what happens? We follow the business cycle. That may be our economy will not expand, that's fast. That is the idea. So these are all related with economic models. Okay. So once we got the idea, then we apply whether the data really confirm that marginal propensity consumption is positive or not. It is greater than some coefficient, some certain level of magnitude. So we test through this data. Once the data we got it, then we estimate this. Then we test the hypothesis. There is no need to say, need to mention to that. Once the hypothesis, the model is perfect, then we go for prediction or we go for policy purpose. Like you might have heard that supply response, supply elasticity, demand elasticity. That's what we estimate. Why? Because it is useful, like supply elasticity. Like usually agriculture commodities are less elastic. That means less elastic in the sense that if you, I would say, one example I say, supply response of cotton. It is a magnitude of the supply response of cotton. That means if you increase the minimum support price, your acreage response under cotton will increase because it's the supply elasticity is so important for us. So like we want to see that what are the crops are price responsive. Basically, we want to see what are the crops are price responsive, what are the crops are income responsive. So we really interested because they have the policy implication. So once we estimate these models, the model is perfect in all the sense, then we go for policy. This is the basic idea. If there is something wrong with that, then again the process will start like that. Okay, so there is no need to say all the thing, though you know that. Then we have in the economic model, usually the economics, our division, deal with observational data. We are not dealing with experimental data. So experimental data, if you have handled, then we would not face a lot of problems. Since our data are observation, like what you have consumed. So these are all, you don't know way to control your consumption. It is no way no one is controlling that you are someone. So in that sense, it's a observational data. So though economics use this model from the experimental data only, just like regression, first we use for experimental data. So then we have extended, we can use it for simple cross-sectional regression. We call it the classical models. Then we have a time series model, like you know that it is also a regression, but it is dealing with like ARIMA, like that model, ARIMA, GARS. So those kind of models are there. So this is a time series model. Another is we have a qualitative response model, something like dependent variable is maybe 0 to 1. You can only yes or no, whether it's available or not, adapted or not adapted. So that kind of question it answers. So remaining independent variable maybe is a continuous variable or is a categorical variable. But here the question is that the dependent variable is 0 to 1. It's a categorical variable. Then we have the impact assessment model, something like if you want to see whether the a variety, if you want to variety yield the old variety and the new variety, so it has improved. Or if you want to say policy intervention, suppose you have made available education to all the people, so you are seeing that whether this due to this intervention, whether was there any change, maybe in terms of income or standard of living. So like that we are seeing, these are the impact assessment models. So different types of model we are handling that. So these are the models. So my objective is here that to bring whatever the since we use observation data, so we face a lot of problems. We cannot all regression assumptions are not fulfilled. So we have some other way how to handle this violation of regression assumptions. So there are so many things are there. We will see that. So first, let me start with when you want to run any econometric model. The first idea is that first we depend on the review of literatures and bring down the research. The basic question, this is a basic issue, but still the people struggle for it, because once you do not know how to frame the research questions, then whatever the model we use it is really a lot of waste process. So the first question is that in the what research question, what is a research issue, identifying a research issue, then we find that what kind of research technique can be, econometric tool can be used, and how we can interpret, because so many tools, it is not RBD, CRD, very standard technique. These are so many techniques are there. So interpretation is a real integration. We have a VAR, so many autoregressive ARMA models are there. So many models are there. So then we come to the relevant research questions. These research questions are very important, because finding research question is so then we come to the relevant research questions. These research questions are very important, because finding research question is use a new data set or study question for a different place, sector, or commodity. Already, if you have we have a data, we have a NSO data. So many data are there. So it's a different data set. So that you can use different new data sets, or you can use, like if you have already studied one question like consumption response or consumption function in one commodity like cereals, you can do it for other. Another question, adding a new variable whose influence has not been studied before. Like example, in our case, usually we have production function. Production, if you take available data, is that all human level machineries and seeds. Suppose we got the fertility data. Now the fertility data, because it's a very important one, that also influence the productivity of production function or the productivity of the crop. So if you have that fertility, or if you, then we can have a research question. There is a new variable. What is the influence of fertility on the production? Like that. If you want to add something like that, if organic production, so organic production is as many things changed. So nowadays organic production. So when that's organic production, the production behavior of the farmer itself changes a bit, because for 3 years he cannot produce a crop. So so the behavior is changing like that. Then try out new or alternative methods to study an old question, something like we have single equation and system of equation, seemingly unrelated regressions, we are using that. So singulars, so like that. And studying an existing question with more recent data. Like I told you that per capita serial is declining. It was the response was different in maybe 10 years back. Now the response is different because we have a per capita income has changed, our education has changed, our lifestyle has changed, so many things. So the recent data is different. So study the questions of policy driven, like MSP, like education policy. So like that, local interest. So like that. So there are so many. What I'm saying here that unless until the research question is not identified, no matter how rigorous our econometric methodology, it is a waste process. So that's why I'm just informing that. So my objective is that if you are I thought that maybe MSc, PhD students would be there, because the problem is that in the MSc and the PhD, they will just go straight to the analysis. That's because I also studied in Angro, Engineering University. Now it's changed in Telangana University. So we have no patience to study the literature review. But no, what happens unless until we don't know how to frame these research questions, analysis is really a very difficult process. Then selecting the right variable, this is what we need the reward literatures. So what variable, if you want to estimate long run consumption or long run productions, so the variable is changing. That variable may not be observed. So we may have current data we have. So like that. So the what rule we have used, that law of parsimony, that you know that is we should explain the model with the symbol least number of variables. That's what our idea is that. So we should always. And another question I think we face in the, I'm just talking about my experience related with this model. We collect so many variables. Our people try to use all the variables. That is a problem. Why? Because agriculture data is, you know that it is a relative variable. Example, if you have quantity, maybe if you apply a rice, maybe 50 kg per hectare, then it may be 100 kg. So there's a proportionality is there in our agriculture data. Machineries or fertilizer you take, whatever the data. So the variables are, if you include all the variables in estimation of the model, whatever, it creates whatever multicollinearity, or is you have excess problem. Even if you estimate some reasonable model, still the degrees of freedom is compromised. So we should not use, because we have many variables. We should use, I think already he has talked in the previous person. He already talked, because it's a multicollinearity. It will introduce a multicollinearity. So what will happen? You need to introduce a variable which has high variability. That variable only we need to introduce. So this should be very keep it in mind that when you select the variables, first thing is that what our economic theory says that. What are the variables use that? Suppose I told you that if we want to estimate the production function, it's a very basic function. Then you need to use physical quantity of output and physical quantity of output and physical quantity of input. If that is not available, then we go for monetary values. Then it should be deflated by inflation or deflator index. You need to deflate it. With the meaning that you are making the variable monetary variable constant. So you are removing all monetary influence in that variable. That's the basic idea. So the idea, theory gives you the idea of what variable to be used. Another is that the variable theory gives us idea that what kind of specification to be used. Example, I told you that in the case of fertilizer response, if you want to study fertilizer response, even experimental data, we do that. Suppose you want to conducting experiment on a fertilizer. Naturally, what happens? certain quantity of the certain point, applying more fertilizer, your response will be increasing. After some time, the response will go down. So naturally, what it says that your theory, what it says that it's something like a quadratic production function, or quadratic function should be used. So this idea. Suppose if you want to use inefficiency, if you want to study the inefficiency, we have a stochastic frontier production function. So what kind of theory gives an idea that what kind of function should be used is this idea. Then next is that next problem, it is if you are using time series data. The time series data, usually what happens many years, if you take Maharashtra, let us take one example. Maharashtra, often this drought comes. There are droughts, they are very severe droughts. Even the severe crops will suffer. So these are all extreme events. Maybe in statistical terms, it may be outlier or influential points. So we need to be very careful on that. So better you remove those. There are times, like I think we might have studied in statistics that, like mean, if you are computing a mean, there are one sample as a very high value. Naturally, all the average value will be affected. So like that only. So the extreme values should be removed. So I'm not going into detail of outlier or influential points. That is already books are available. So you just check that. Then I told you, then we have a transformational variable. Maybe suppose some variable should be in squares, some variable should be in cube, some variable should be in inverse. Inverse, we should express in inverse function. So these kind of things we should what variables should be needed, that we should before all these things, using this review of literature, we should finalize all those things. Then only we can go for econometric methodology. Otherwise, these are all basic. It is something like a plan, the living plan. Without living plan, whatever the technique you use it, the plan will not work. So the same thing like that. These are all basic pillars on which our economic methods are standing. Then, I don't know, problem is that I'm talking about the students and the scientists also. What happens, the sample size, usually when I attend the training, people always ask, what is the optimum size of sample, what is the optimum sample size? Whether it is 30, or someone says that if you add one variable, number of for each variable have 10 observation minimum. So there are so many things would say that. I am not a statistician to say that what is the sample size. I am not going to generalize it. But I will tell you that if you are taking any project, don't come down less than 200 or 300 observation. It is my experience. I really, as a student, I studied, I run a model with 100 data. Then I struggle for savings. No, it won't come. It is a headache, big headache. If you just see the international papers, the number of samples they collect, you see, you don't, most probably we are state agricultural university, we have budget constraints, and then we go for lesser samples. It is I would say that don't compromise on sample size. It's really difficult things. The greater the samples, then the significance of the variables are good. A lesser sample, you have to struggle a lot. You need to do a lot of combinations. So that would be very difficult to work. So larger the sample, result in increased power also. So let us be very careful on that. Otherwise, how many models, what kind of econometric models are not useful. Then this is already, I think you might have already covered that. What happens, our people start that they will study the review of literature and what model they will use, and they will directly go for econometric model. So, but it is not so. First, we have to start with, see whether is there any data entry or just plot the data, whether any data entry errors are there. Then you check it. Let us see that whether one variable, if you see that histogram, or a two variable, you see that is a scatter plot. To see that whether the observed relationship, whether positive or negative or no relationship. We need to see that, because many times we go straight to the model, then we don't when you estimate the model, what happens? The model may give one time positive value, then maybe multicollinearity something, and it may give negative value. So we have no reason that what is the value of the coefficients. So this should be confirmed. If you want confirmation from your heart, better you start from the beginning, like a two variable, like a given tablet. You make a scatter plot. So like that, we should do that. Then only we can confirm that consumption, production and input, like let us say output and fertilizer application, positive relationship. Output and labor, it's a positive relationship. So we can do that. Otherwise, we are not sure what would be the model. We just believe what the regression result is being reported. We have no way. So I think we have to start with the beginning. So we should not just jump to the model. That is, we should resist that urge. Just I am taking a small example. It is a simple regression. I think probably you can understand it. What it says, the PC simply indicates that personal consumption expenditure, per capita consumption expenditure, and it is a PDI is a per capita disposable income. It's a two variable. Per capita consumption expenditure is a dependent variable, and disposable income PDI is an independent variable. So we have a macroeconomic theory says that consumption is a function of income. So we have used that. So we have, based on that, we have arrived this variable and we have run the model. So there is no need to explain to the statistician. So you simply, it says that we have coefficients, intercept and the slope, also associated with standard error. Then we compute the t-value. T-value nothing but coefficient divided by standard error. Then p-value, based on the t-value, we compute the p-value, whether it is a two-type test or one-type test, depends upon that. So this is our regression output. It is for two symbol regression. You can add the variable also. Can add. So now, how we judge these models? The question is that we can run many models, but the question is how you are going to judge whether the model you run is right or wrong. That is because this is what you need. Ultimately, you are going to use that model for policy implication. That means the policy, those who make policy, they are going to use it. So if they want to believe in it, so you need to cross-check. You cannot simply run because I'm a statistician or econometrician. Simply I run whatever the model, I got it, and I cannot give the estimates. It needs to fulfill, there are many criteria. So first criteria is economic criteria. It's not a statistical criteria for us. What do you say that, let us say, I told you that now we are running, we are seeing the sign and size of the coefficient, because our theory, both economic theory and the mathematical economics gives fair idea about what is the sign of the coefficient, what is the size of the coefficient. It gives some idea, like elasticity. If you want to estimate the elasticity, the values are between 0 to 1 mostly for agricultural commodities. It cannot be more than 1. For luxurious commodities, they are elastic commodities. They can be greater than 1. So it gives idea. So inelastic should be 0 to 1. So it defines the range of the coefficients. So in that way, in this example I am running, Keynesian macroeconomic theory predicts that marginal propensity consists nothing but our beta 2. So it should be positive, and it should be so one more idea is that long run MPC should be greater than the short run MPC. So like that, economic theory and mathematical economics give some idea for us. So we should decide based upon this idea. This is a basic principle. You cannot straightly, since my model is significant, I will go to, I cannot give to policymaker, or I cannot just publish it. So it is not possible. So first, the verification, the first rule is your economic criteria or your economic theory. Okay, so we should not just go straight to the model. That's what I'm again and again I'm saying that when you model it. So second comes the statistical or economic criteria. Is the second one, like you want to see the significance, whether the coefficient is significant, whether the standard error is minimum. So if you have estimated so many different multiple regression, then you see that you are testing the joint restrictions. So you are testing the hypothesis of all beta coefficient. It's not. We will see that in the later part. So we have to decide on that. So statistical or economic criteria give us the idea. So it simply gives us a reliability of the estimates of the parameters. Then you need to check whether all assumptions, OLS assumptions or model assumptions have been fulfilled or not. Example, I tell you that we may be knowing that all OLS assumption, there is no multicollinearity, there is no heteroscedasticity, there is no autocorrelation, there is no specification bias, there is no endogeneity bias. So all these things. Similarly, if you go for cointegration, and that's integration order of all the variables used in the regression should be same. That's the idea. So these are the statistical criteria. So these are all comes seconds. So these are the way we judge what are the model we have estimated. Is it reasonable? Is it valid? We are using these economic and statistical criteria. Okay. Now we happen that sometimes we estimate the model, it gives the wrong sign, the unexpected sign. So what could be the most possible reason that? One is that some regressors are too small. Other maybe we have we have not added enough variable, or we have not added the right variable, or maybe it's multicollinearity, we add more variable. So either case it can be. So, but it simply gives us the idea, but it never said that which variable causing the wrong sign. So that you can see in multicollinearity or the specification bias. We have to put the special chapter in economics. We have to study that. So already he has that Yadav sir has already covered it. What is the reason for multicollinearity? I'm not around that. So now, how to improve this model? Once we have estimated the model, okay, there is reasonable values we have obtained it. Now, how we can improve it? First, I told you that I think you got it. We have to start from the theory. That is over. Another is that we have to see that test of significance. There is no need to explain to the statistician. So whether this Indian coefficient is significant or not. Then theory gives the idea that right specification of the model and the transformation of the model. Then one more thing. These are all the things. Usually I'm talking about now, apart from the statistics like multicollinearity and the heteroscedasticity and autocorrelation, we face endogeneity bias. What is endogeneity bias? See, endogeneity bias simply say that there is a relationship between your independent variable and the error time. Let me explain you a little detail that. Then this is a major detail. Example, I tell you that. See, example, you have a field. You are a farmer, let us assume that. If the land has a fertility, good fertile land, the way you behave is different from the land is infertile land or the rain fertile land. Because in the rain fertile land, you say you won't take care of all the operations. You just go and throw the seeds. If it comes, it's okay. Otherwise, leave it. That's right. But if it is a fertile or the good irrigation land, what do you do that? You take care every effort. You labor, you fertilizer, you take effort. So it's if you are not include the fertility of the soil or the irrigation status of the land, then you are committing your error. There is an error, variable you are not included. It causes that the error is related with your other variable, because the variable like fertilizer application. There is fertility, influence your fertilizer application, the labor application, the your so many things. It has some relationship. So in that way, it is endogeneity bias. So once the major issue we deal with it, apart from that specification bias, we do that. Remaining things is as usual you deal with in statistics like heteroscedasticity and autocorrelation. Since the others are already covered that. So if what happens, there is a heteroscedasticity, we cannot do one thing. We can just make the standard errors is so efficient. We just minimize the standard error. Like the same way we correct this standard error. So there are many methods are there. We just use that and compute that, and we can do that. But these are what I'm talking about. The endogeneity bias and specific bias are econometrics point of view are very serious. Then let us take one example. I'm just starting the theory. I told you that production is a function of labor, capital, energy, material. These are all theory, this idea. Similarly, profit is a function of output price and price of input. So these are all ideas. So once you got that, you just testing the with the data you are with the appropriate data, you are testing those models. Okay. So now theoretical proportion provides the basis for econometric study. So it is useful to investigate whether the theory is consistent with the other principles. So whether consumption and income relation is linear or not. Just like if you want to say that consumption function, whether it is a linear relation or non-linear relationship. One more thing, that whether the parameter you estimate is stable or not stable. Example like that there could be a structural change, like liberalization. It happened in 1990. So the way fans industries behave, because now all the things are open. So industry behave, the behavior of the industries is different from the previous period. So naturally, the parameter not going to be stable after period. So we have to remember those things. Whether any other factor can improve the relation between consumption income, apart from per capita income. So is there like, if suppose let us take per capita income, if you take inflation. The more the inflation, naturally what happens, you need to pay more interest. So the consumption, your income is lesser. Or if the more the tax, your income is going to be reduced. So like that. So any other variable to be included in that model. So this variable we have to be very, we all we get it from the theory. Then another is that specification of the model. So there are, even I told you the endogeneity bias. Like if you take output and prices are, if you model a output or prices, you cannot use single equation, because we know that supply curve and the demand curve, they interact, they decide the output quantity and the prices. This is a basic economic idea. Then what you say that output and the prices are to be jointly determined. So the idea is that you cannot estimate this relationship with a single equation. If you are using a single equation, if you are modeling a price with the single equation, or supply or demand with the single equation, you are committing the endogeneity bias or simultaneous equation bias. So we have to be careful. So in that case, you need to use system of equation. It's something like that. When you can use a single equation, like only X affect the Y, but Y doesn't affect the X. It's something like rainfall influence the productivity of your crop, but productivity of crop now are going to affect your rainfall the same way. In that case, you can use single equations. So it is all the independent variables are exogenous. In that case, you can use single equation. But in our case, economics mostly is a variable should be determined jointly. In that case, you have to use simultaneous equation or system of equations. So we need to decide. So what is the appropriate function? It is a single equation model or a system of equation model. Then whether it is a model, once you estimate it, it says that there's a model parameters are constant or not. So these are all the specification bias. What are the criteria? then only we can say there is no specification bias. Another is that exhibit data coherency. It simply mean that residual estimated from the model should be purely random. If your variable, if your residual is not, it follows some pattern, it is something like you have a cane, sugar cane. Your residual, something like your, what do you call, after processing your juice, what you are left with the residue. There should not be the residue, you know that. If the residue, something juice is there, then your process is not enough. So in the same way, same logic we are applying here, that the residual should be purely random. There should not be any juice in that. There should not be any variation in that. So we should remove all the things. Then de-encompassing, that means that the model cannot be, the model cannot be improved over the chosen model. So you should explain all the competing model. You should know more, has a more ability than other competitive model in that sense. So, but usually what are the error we commit in that? Mostly what happens, we may not include the right variable. Probably we might have not collected those variables. And we might have included more variable, since I told you that, because I have more variable on that. Then wrong functional forms, maybe a measurement error. So the way you have measured the output and the independent variables and the dependent variable, it matters a lot. So there are sets of tests are available, like examination of residual one way, or diagnostics and statistics, run say reset test. So these are to identify the specification bias, we use just, there is nothing, I'm not going to explain all the details of this, how to conduct a Ramsey reset test. You just write a code on, or it will tell you that whether your model has a specification bias or derivatives and statistics. So these are gives some fair idea for that. So there is no need to explain all the detail. Then already explained that what is a single equation and the system of equations. Next is endogeneity bias. This is very need to be even very important one we often face in our estimation of econometric models. So it's refers to a situation in which exponent variable is related with error time. Basically, it's a violation of the assumption of classical linear regression, that is zero covariance between error time and the independent variable. So just let us take one example. Just I'm taking a Cobb-Douglas production function. So I think probably how many of you know this? Is a y is a function of we have x1 raised over alpha 1, x2 raised over alpha 2. These are also just elasticity. So just you can linearize this. It's a nonlinear function. You can linearize. You just take logarithm of both sides. So in ln y is equal to ln a plus alpha 1 ln x1 plus alpha 2 ln x2. So this is the simple Cobb-Douglas production function that we often use it. So our economic theory gives the idea that I think probably if you remember your output input response goes up. So we know that there is a marginal product. There is your rate of change in your output with respect to input is equal to 0. That is the peak of that function. So that is equal to 0. That is a function. If there is no input constraint, there is a place you try to apply your input. But there are cases if you have a budget constraints. So what you do, our economic theory said marginal value product is equal to marginal factor cost. That means that marginal product, that is nothing but dou a by dou x1 times price of y. So the marginal product multiplied by the value of output is equal to marginal value product. That should be equal to marginal factor. You simply say that additional return should be greater than equal to additional cost. That is the simplest way to say that. So that's the way. So it is an idea. So our economic theory gives an idea that marginal value product should be equal to marginal factor cost. Marginal factor cost, I say that price of input. That's why I say that additional revenue, the marginal revenue should be greater than that of the additional cost you use, the same logic you have to use it. Okay. So once based on that, using that, just I'm rearranging the term, just taking that input demand is equal to nothing but alpha plus it's a marginal value product. It's something just rearrange that equation. Just you see that this equation and just I'm rearranging it in such that input is equal to revenue divided by input price multiply production elasticity. So this is the idea. So we just take in the natural logarithm. So what it says that this x has related, I think probably a double plus is just kindly forgive me, these are typological errors. So this natural log of x1 not only depend on this alpha I py divided by wy, it depends on y. This y, you know that it's also influenced by the error term. So this x1 influenced by the error term. So it is a endogeneity bias. Simply says that when you cannot in observation data, you just simply estimate the production function, you will end up in endogeneity bias. So what you need to do? Better you go for it is a primal approach. You can go for dual approach or some other way, or you go for experimental data. So naturally, you won't go for experimental data. You don't have that much access for the data. So if you have experimental data, you use it. Estimate production function. There's no issue on that. There is no endogeneity bias on that. So we have to be very careful about this endogeneity bias. Then is another issue we deal with this selection bias. Is usually happen in like impact assessment studies. Like example, if you want to study drip irrigation adapter. So what happened drip irrigation, or if you want to study about the smoke response. So if you want to study response of non-veg consumption. So what happened? Let us take a small example. If you want to study non-veg consumption in determinants of non-veg consumption. So one thing that you will collect the data who consume the non-veg data, non-veg. You can't connect the non-veg consumption quantity from who doesn't consume the non-veg. So like that. So when you select the participant, the samples, it is it is something like you are biased sample you are taking that. It is, let me read it. Now the sample selection bias arises as a result of selecting samples or persons who are not equally representing the population. I told you that in this case, non-veg consumption. You are selecting a sample who are consume more non-veg. You are not selecting the person who are not consuming the non-veg. So the population is not equally represented. So for that, what we do, we use Ekman correction. It's a two-step statistical approach only. I'll tell you what we do that. The first stage, the Ekman correction, we estimate the function just suggested by economic theory. Then the researcher formulates the model based on the economic theory. One thing is important, that the dependent variable here, yes or no, or you simply are using the logistic or probit regression. Okay, so you are estimating that, the first stage. The second stage, from the probit function, you compute inverse mill ratio. Once the inverse mill ratio is computed, you just include in the model. This is how we are estimating. Just I am taking one example. You can take it here. Second stage, correct the set selection by incorporating inverse mill ratio as an additional explanatory variable. So it is a kind of a fish demand estimation. What do you do that? We just create a variable like goat consumption, per capita consumption, greater than 0. Then we run a probit regression. I hope it is probit. We are running a probit. It's a stata code. Probit is function of x1 and price of fish and price of goat, price of pork, price of poultry, price of eggs. So these are all our economic theory, the independent variable suggested by our economic theory. So once done that, you are pointing out inverse Miller ratio. I think probability density function of probability model and cumulative density function of probability model. So taking the ratio, you are getting inverse Miller ratio. Once you got it, you use it in your actual demand model. That is, model is share of fish consumption is equal to price of fish, price of goat, price of pork, price of pork, poultry, egg, and so all these things. So plus inverse Miller ratio. So this is how we avoid selection bias. Right. Another is that another selection bias is that propensity score matching. It is a kind of a quasi-experimental method. The idea is that we are constructing artificial control group. How? By matching each treated unit with a non-treated unit of similar characters. Just I would, it is as to visualize, I will tell you one example. If we have a fraction like 3 by 4, in that you want to minus the half. So what you do, you just denominator, you raise the denominator equal. That's how we do in our arithmetic. The same way, the same logic is here. Usually what people do that, suppose adopter of micro irrigation and non-micro irrigation. So what we see, usually we just see the ecosystem or the district nearby, and then we just make the comparison. How many people have adopted, or how much yield they arrived in the adoption, and how much yield arrived in the non-adoption area, and take the difference. That's how we do that. But here, what you say is that no, not like that. That's wrong, because there is a selection bias. What it says, you see the base, select the you create a score based on socioeconomic variables or covariates. So like education, experience, and connection with the extension agent, and he's a good for, he's a big farmer, small farmer, so like that. So based on that, you see that what is his propensity to adopt. See, we have the data, both the adopter and the non-adopter, and their characteristics. So it based on that, you see that it creates propensity scores. Okay. Once the propensity score is generated, based on the score, your adoption response, the treated value, is being compared. So it's a basic idea. It's a basic idea. So what do? The steps I have given is select covariate. Select covariate means I told you that the variable, socioeconomic variables, and select the model for creating propensity score. So usually the logic model, and select the matching method. There are many methods out there. I'm not going into detail. It's a neighborhood method, cluster method. So many methods are there. So then once based on the matches, propensity scores are created and balanced, then you estimate the effect. You just find out based on the score, you compare. If suppose the adopter propensity score, he has a X, and the non-adopter X, the value should be compared. Then only you can compare the treated. So equally balanced. I mean that it's something like in karate, people fight equal weight. The junior fight with junior, senior category fight with senior. The same way. So it is a junior to junior and senior to senior. So in that way, we are using the propensity score. We are creating a balance. Then you make the difference in your treated value. So it's a basic idea of propensity score matching. Okay. Then another is that we often deal with it spurious regression. It is when it is like when there is no suppose there are variables out there, but you don't expect there is no meaningful relationship, but still the coefficients are very significant. Suppose the person is very statistical minded like me, economic minded, we think that, whoa, what is some relationship? There could be a theoretical relationship, just excited. But the theory very clearly says that if there is no meaningful relationship, first you don't see the meaningful relationship. So you find that you need to question maybe that kind of relationship is called spurious relationship. Maybe the R square is high, the beta quotient is significant, yet the variable has no meaningful relationship. So in that case, it is called spurious or nonsense regression. So I think it's usually this concept comes around when you use time series models, not necessarily time series model. Even you use a variable like price or price, whatever the time series data you are using. It very severe when you use financial data like stock price, stock data, those kind of things, or RB data or RB aggregates. What are the aggregate they collect? Those things are shows more number of nonsense regression. Let us come some basic idea. You probably might be having. You know what is stationary series and non-stationary series. Just I am reminding that stationary series means the usually all the moments of the like mean, variance, covariance are constant. That is a strong stationary reason. Usually when econometrics we deal with weakly stationary. That's what we mean. That means mean and variance are constant. That simply say that they are time invariant. Example, your rainfall data. Rainfall data will never go is up and down. It is if you take the 10 years, the average is average only. It never goes. Even the variance is constant. But if you take the production data or the consumption data, I am talking about the aggregation. So it naturally goes up. Even if you take the per capita per capita consumption, in the when you are small, less you consume. When you are young, you are considered more. When you are old, you are considered a little less. So there is a way the mean and the variance are going to be varying. It's a time. So it's a when the variance and mean are not constant, we call it non-stationary variance. One more concept I want to use that. How many times you need to take the first difference so that your non-stationary series become stationary? That is called integrated order. Suppose say that there is no need to difference the data. Your data is already stationary. We call it integrated order 0. If your data need to be you need to one time you need to take the first difference to make a stationary, then that is integrated order 1. If you need to take more difference, so integrated order m or 2, 3 like that. So this is the non-stationary series. And stationary series can be named as like integrated order 0 or integrated order greater than 0. Now we have a unit rule. When the stationary non-stationary series you have, naturally what happened, they have the unit rule properties. So like that, you just take this example, yt is equal to rho times yt minus 1 plus ut. So the rho value lies between -1 to 1. When it is 1, I'm saying that when it is 1, simply says that you are variables accumulating the shocks, the residual are the shocks, keep on accumulating. So your variable is not going to be nowhere going to be stationary. It is going to accumulate, it is keep on increasing. So there is usually non-stationary series are called unit series. These are very important. Why? Because we have a time series regression that is called cointegration. If you want to estimate the cointegration, the minimum requirement is that all the variables you are using should be same order of integration. I told you that. What means this order of integration? In the number of time you need to take first difference to make the variable stationary, right? So if you are using the time series variable, both dependent and the independent variable should be same order of integration. Or like say simply to say that logical sense, the person is cunning, man is cunning, his wife also should be cunning, then only the family can run. The man is good, right person, the wife should be good, then only the marriage can be stable. This same logic we can use it. The non-stationarity, the order of non-stationarity, integrated order, so it should be same. Then only you can find the longer relationship. Another way says that if the two variables should be cointegral if they have long run or equilibrium relationship between them, are residuals from the regression are integrated order 0 are stationary. These are pure random. That's what I am talking about. We have talked about pure random. Integrated order 0 means simply it's a pure random. So the meaning that the variable can be what variable? It can be a integrator 1, 2, 3, no matter. But what is the residual? You obtain it. The residual should be stationary or integrator 0. Then we call it that regression is a time series regression, or we call it a cointegration relationship. The parameter you estimate co-integrator regression coefficients, regression coefficients. Okay. So it is simply indicate the long run relationship. So what happens? There are times people will do take the first difference of this variable. Since the non-stationary variables are non-stationary, some people may suggest that you can take the first difference and run the regression, you can get the same value. What happens? You lost the long run relationship. The beta coefficient, you lost it. When you take the first difference, you are running the short run relationship. So we need to be very careful. Yeah, so that's why we have a special econometrics project called regression is one. So there are steps are there how to do. First is you have to test for unit root. Make sure all the variables are the same order of integration. Unit roots like Dickey-Fuller test or augmented Dickey-Fuller test. Still there are so many unit tests are there to see that whether the variable are same order of integration. Second, once it is done that, you need to verify that. Then done that, you can run simple regression. I'm talking about Johnson co-integration method. So in the Johnson co-integration, just simply a regression. So you take the variable and test the unit root and run the regression. So and take the residuals. Check the residual whether it is stationary or not. You should be stationary. If it is not stationary, suppose assume that one variable is in a different order of integration, then naturally you get the residual is not, it won't be a stationary, it will be non-stationary. So what you need to do, I told you that you should be same order of integration. You can meaningfully transform the variable. Example, what you can do that, there is some variable, you can make it as a growth rate. So it's taking the ratio of the variable. So somewhere you are meaningfully transforming it so that when you take the ratio, the number of hours you need to take become lesser. So in that way, the thing is that whatever you do it and make the residual is stationary. So once you have done that, and then you stationary, you can claim that regression and that relationship is longer relation. Once that is over, you can estimate. Once the longer relation is there, always there is a shorter relation will be there. So you can do that. You take the first difference of both the variable and add the lag of your residual times and run the regression. That is called error correction mechanism. That's what we call it. So it is simply it says that shortened relationship. Okay, this is what we are doing. So it is one example. It is not a co-integration. It is I used it in linear regression. What we did, we are trying to understand what is the determinants of gram production. So we had a rainfall and the yield and irrigated area and revenue difference between the wheat and the gram. So when the variable, one of the variable is non-stationary or the order of the variable is not same, what happens? Your residual will not be stationary. When the variable residual is not stationary, you cannot apply usual inference on t-value, that is the distributions are biased. So you cannot, whatever the your inferences is going to mislead you. So in that case, what we have done that, in the RD variable, it was a integrated order 1, it was coming, and remaining variables are in the stationary variables. So what we thought that we convert them into growth rate. So then we run the regression. In that way, you can make it the variable meaningfully. You can transform this variable. So this is the idea of that. So then this is hypothesis. There is no need to explain for you. We test hypothesis. But one thing that we do that usually we do that set of regression coefficient. Just I'll tell you one example that. Like if we estimate the production function, we often worried about whether return to scale is 1. Right? Simply the meaning is that If you increase all the input in the same proportion, your output will increase the same proportion, because it's a more policy questions. See, like you have a reti or a crop. If you are increasing the same proportion all the input, your output decreasing, increasing at lesser proportion than the input proportion. Simply, that means you have to apply more input. That means it's a cost of condition very high. They use in other way that, suppose if a return to scale is greater than 1, that means your output increases greatly than your input proportion. Simply that you have a people, your farmer will be very happy because your cost is less, your production is high. So it is a very useful one. So we need to test that whether your Karl-Douglas production is return to scale is 1 or less than 1 or greater than 1. You need to test it. So we do that. So what we do that, we take the production function and we estimate unrestricted Karl-Douglas production. Suppose let us say that production is a function of labor, capital, and material. We run that. We estimate Karl-Douglas production function. Then the second, that is first step is over. Estimate the unrestricted Karl-Douglas. That's over. You can do that. Second step, we estimate the restricted Karl-Douglas production function. I'm sorry, I'm taking more time. I just made 5 minutes. I have more than I want to take. You just impose sum of all your coefficient is equal to 1. So that's the idea. So once you do that, you just substitute in your equation and you arrive the final equation. This is your final equation. I'm just giving the color. So it's your final equation. So it is a restricted Karl-Douglas production. Once that is done, you just test your F-test. Based on your F-test, you can see that whether your actual phenomenon is, or the production behavior is following the restricted production function or unrestricted production function, or it is following a concentration scale or no concentration scale. So you get some policy question, you are able to answer it. Another is that we typically use that translog production function. The problem is in Karl-Douglas production function is that it's a elasticity of substitution is 1. That means the substitution between the input is in same proportion. That's the idea. So here we have used the translog production function. You can take into that variable substitution in that respect. We have done that. So we are imposing some idea. So just impose the constant and scale. We have different restriction. So we are getting that like that. We find out the restricted translog production function. Then we apply the F-test. So in that way. So what is the response or behavior of the production? What is the production behavior? It's just empirically verifying this production behavior through this. So we are using this set of coefficient restrictions. I think probably, did you see that? I think probably did not share it. I think, how did you see that? One more thing, we little worried about this one-tail test. Usually our economic theory direct us whether the coefficient is positive or negative. So in that way, we use that one-tail test. The idea is that, suppose I am taking that. See, we run the regression. The coefficient p-value is 0.08. So what happens if it is 0.08? It is not seen at 5% level of significance. So what you can do, if you conduct only two-tail, usually the software gives a two-tail test. So if you conduct one-tail test, what you need to do is just 0.08 divided by 2, that will give you a 0.04. That's one-tail test. It simply says that your coefficient is significant. So these are very significant for statistical science. These are very important things. People may not realize it. Another is that hierarchical model, the mistake they can do that. See here, introduce x and x square, the polynomial terms. Then, when see the significance of the coefficient. Suppose x is not significant but x square is significant. Just they remove the x and only use the only x square. But that is wrong, because x square comes from the x1. So the thing is that when you use the polynomial, the lower order should be kept unless until we have the proper justification. So these are some of the things we face in modeling the econometrics model. So some of the issues I have not dealt with all econometrics is very difficult. I'm not that hardcore. But the thing is that I try to help you. What are the model? What are the violation? What are the problem we face, and how we can just solve it. So this is what I want to share with you today. Well, I'm done with.
Thank you, Dr. Kingsley,
Yes,
for
sir.
a very informative and in fact, I know this topic is somewhat new. In fact, for many of us, including me, many of the faculty too, sir. You know, from how this economic theory is related with how you involve this mathematical theory and how ultimately economic model developed. It is a really, in fact, it's the first time for me to see such kind of beautiful example. So I request Dr. Arvind for vote of thanks.
Thank you, sir. Thank you, Dr. Kingsley, sir. Sir, we know that it is very difficult to present such type of topic for heterogeneous audience, but you present it very well and in digestible manner. Sir, on behalf of our organizing team and from the Navsari Agriculture University.
Sir, can you stop your screen share?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Please.
Stop. Sorry, let me just give me time. Stop share. Yes, it is here.
Sir, just as a token of gratitude and as a thanks, we are presenting this. Once it is signed, then it will hand over to, or in fact, email to you. Arvind, Dr. Arvind, we cannot hear you. Please unmute yourself.
Yes, sir.
Okay. Now, please continue.
Okay, thank you, Kingsley, sir. Now I am audible, sir.
Yes,
Yeah, it is audible.
Okay, sir. Sir, we know that it is very difficult to present such type of topic for the heterogeneous audience. But Kingsley, sir, present it very well. And we are thankful for this nice presentation. Sir, behalf of our organization team, we, as a vote of thanks, I am presenting this certificate to you.
Thank you, sir. Thank you.
Thank you, sir. We are grateful to you.
I hope you got something.
Thank you, sir.
Thank you, sir. Thank you.
Thank you,
Dear
sir.
participant, you just listen very intellectual scientist, Dr. Kingsley, sir. He explained about the basic concept of econometrics and linear programming, and also the very well discussed the common error associated with these types of topics. Thank you, sir. So we have completed our morning session, and we will meet for the last session of this event in afternoon at 2:30 p.m. So please rejoin us for the last session. Thank you very much.
Thank you, sir. Thank you. Bye.
Thank you, sir.
There is one announcement for all the participants. Their feedback form is supplied to you around 2:30. So please fill that form. And once you fill, certificate will delivered at your registered email ID. And don't because certificate will be delivered 100 per day. Okay, so within 5 or 6 days or maybe 7 days, because around 700 people get registered for this webinar. So sooner or later you will get your certificate. So please have patience. Once you have filled this feedback form, then you will get the certificate. So we will meet around 2:30, 2:15. So please be with us. Thank you. Welcome to the second session of second day's webinar. Friends, very soon we're going to start our session as our speaker have some internet issue. So once he connected, we will start. So please be with us. Thank you.
Oh, hello.
Dr. Nitin, can you hear me?
Yes, sir.
Okay. So our next speaker is joined now, Dr. Sudhesh Srivastava. So I would like to request you to please introduce him about yourself.
Okay. Good afternoon, everyone. I am Nitin Vashne, Assistant Professor, College of Agriculture, Bagai. Very good afternoon to one and all. I welcome all of you in afternoon session. In morning session, we have a great talk on regression analysis and econometrics and linear programming by Dr. S.K. Yadav and Dr. Kingsley. Now we have with us Dr. Sudhir Srivastava, sir. He is my senior also from IISRI. Dr. Sudhir Srivastava is working as a scientist at a Center of Agricultural Bioinformatics, IASRI. He did his master's degree in agricultural statistics from IARI, and he did recently he completed his PhD in interdisciplinary studies with a specialization in bioinformatics from University of Louisville, USA in 2019. For that, he awarded with Netaji Subhash Chandra ICR International Fellowship. For that, congratulations, sir. His scientific interest includes statistical aspect of bioinformatics and computational biology. At present, he is associated with various research projects. In addition to this, he is also involved in teaching of MSc and PhD bioinformatics students of PG School IARI. He's published 16 research papers and 1 book chapter and various popular articles. He's project in charge and co-PI of various projects at IASRI. He's an expert in statistical data analysis and well equipped with various software tools and methods to analyze high throughput omics data, that is genomics, transcriptomics, and proteomics. It's my privilege to introduce such an eminent young scientist to deliver a lecture on analysis of proteomics data in presence of heterogeneity in a special reference to missing values. Over to you, sir. Welcome, Sudhir, sir.
So, am I audible?
Yes, sir.
So thank you for such a nice introduction for me.
Thank you, sir.
So should I start my lecture?
Yes, sir. Sure, sir.
Thank you, Dr. Alok Srivastava, for giving me a chance for delivering a lecture. So should I start now?
You can share your screen, sir.
Okay, so I'm sharing my screen. Okay. So, I will share another screen.
That is.
So are you able to see the screen?
Yes, sir, it is visible.
So, okay. So now I will give a lecture on proteomics data analysis in the presence of heterogeneity, and I'm giving this with reference to missing values. So this is the title: Analysis of Proteomics Data in the presence of heterogeneity with special reference to missing values. So first, I would like to give introduction about proteome and the proteomics experiment. So the term proteome, it is defined as the entire set of proteins that is produced or modified by a living organelle. And this proteome, it never remains constant, and it always changes from cell to cell and time to time. And so in most of the proteomic study, we are dealing with the large scale quantitative or qualitative study of proteins, and it has various application across various fields such as biomedicine, agriculture, and animal sciences. And some of the practical applications are given here, such as this is used in expression proteomics, in the discovery of biomarkers, and the structure proteomics, and studying the interaction proteomics. These are some of the basic applications. And here I am giving an example with respect to plant. So these are also important for studying the various aspects of plant functions. For example, the identification of candidate proteins involved in the defensive response of plants to biotic as well as abiotic stresses, and it can also be used for studying the effect of global climate changes on the crop production. So these are the examples in plant. And the proteomics expression, that is also called proteomics abundance. These data are generated by using recently developed high throughput technologies, and these usually involves a mass spectrometer. So there is a method called LCMS, that is liquid chromatography, which is coupled with mass spectrometry, and this method is used for identification and quantification of the peptides and the proteins in complex mixtures. And so the experiments of proteomics, there are two major approaches. First one is the bottom up, and the second one is the top down. So in the bottom up, so in this approach, so we take a sample, and in this sample the proteins are digested using some enzymes into peptides just before performing the mass analysis, and after that we use the peptide masses and the sequences for identifying the corresponding proteins. So here, so in this we are just digesting protein into peptides, but in the another approach, top down, here we are analyzing the whole proteins, and we are calculating the mass of the whole protein and their fragments for identification. So these are the two approaches of the experiment. And the features such as, so features can be at two levels, that is, it can be at peptide levels or protein levels. And so their quantification can be done by two major approaches. One is the level free and another is labeled. And in labeled, there are three methods: metabolic, enzymatic, and chemical methods. And these are used for detecting the differences in the feature abundance among different conditions. And so here in this lecture, I will mainly focus on the level free quantification method. So in this, there are another two methods, approaches. One is so we are quantifying the data using the MS ion intensity, and another is the spectral counting of the features. So these are two major approaches. And so earlier I have just give you basic introduction about proteomics, and now I will give the introduction about the missing values and the data heterogeneity. So in the proteomics experiments, the data, it may consist of only the biological replicates, or it may consist of biological as well as technical replicates. So we are taking the biological approach for studying the variability, biological variability, and the biological variability arises from the genetic and environmental factors. And while conducting the proteomics experiments, so there are various approaches. So step by step, such as sample collection and the sample storage. Another approach is, another step is the sample preparation, then extraction of the samples. So it can be extracted from the like liver tissue or the kidney tissue. So, and the next step is the LC separation and MS detection, that is mass spectrometry detection. So these are the technical approaches. But while collecting the data, so there may be variations. So there are two types of variation, that is biological variability and the technical variability. So due to this, there is some data heterogeneity, and so this is one of the challenges analyzing the proteomics data. And another problem is the missing value. So suppose we have two groups like case and control, and we have equal number of samples, then that type of experiment is called balanced. But if we have unequal number of samples in two groups, like in one sample there is five samples, in another it is 10 or 8, so that is unbalanced. And in that situation, we have to use the proper statistical test. So in the proteomics experiment, the data can become unbalanced. It can be due to availability of unequal number of subjects, that is the samples, or it can be due to the missing values. So there can be missing values for a peptide or a protein, or and the unbalanced data can also be due to the like unequal number of samples as well as missing values. And the missing values generally occurs due to biological and technical reasons. And in the proteomics experiment, so we have very high percentage of missing values. So it ranges from 20 to 50%. 50%. So there is experiment called microarray. So in that the missing percentage is less, and here we are getting more high percentage of missing values in the proteomics data. So there are three broad categories of the missing values. First is the missing completely at random. Another approach is missing at random, and third approach is and the third category is missing not at random. So in the first category, MCAR, so here the missing values are independent of both the observed and unobserved data, and these originate from the random errors or the stochastic fluctuations. And another category is the missing at random. So here, if you put some condition on the observed data, so we can define the missing values based on the other observed data. And third is the missing not at random. So if the data is neither MCR or neither MAR, so in that case we call it as missing not at random. And so for each, so the machine, like for getting the data, so there are some limitations. So because some of the features that cannot be quantified because they are below the detection limit in some of the samples. So due to that, we can also due to that the missing value can occur. So when the features are having the below the detection limit. These are three broad categories. And so for getting any analysis, we need the complete data for the analysis. But in case of proteomics experiments, the presence, so we have many missing values in the data, and which prevents the complete and accurate analysis of the proteomics data. So the missing values and the data integrity are the major challenges. So this is an example of proteomics abundance data. So this is the spectral count data. No, it is spectral intensity data. So data can be of two types, like spectral intensity and spectral count. So I'm using the spectral intensity data. So in this, so there are three groups: group 1, group 2, and group 3. And within each group, there are three samples, biological samples. So this is dummy data set just for demonstration. And in the first column, there is called protein. So the first column is the protein, and the second column is peptide. So like, so for a particular protein 1, suppose there are six proteins corresponding to 6 peptides corresponding to protein 1. So for protein there can be various peptides. Similarly, for protein 2, there are 5 peptides. For protein 3, there is only one unique peptide. So, and the experiment can do the analysis either at the peptide level or the protein level. So, and so as we know that with the introduction of the high throughput technologies, we can generate the proteomics data more reliably, and that can be analyzed using the various statistical approaches. And the basic steps for analysis are: first is the feature identification and quantification. Then the second step is the data pre-processing, that includes the normalization and imputation. Third is the abundance analysis using appropriate statistical test, and the last is the data visualization, and we can also further do another analysis like network analysis or annotation like that. Is further annotation. So these are the various steps. And so for performing any statistical analysis, first we have to properly so the first step involves the summarization intensity of the features using a quantitative summary, and we are using some transformation such as log transformation so that the data should become normal. So this is the first step. Suppose we want the analysis at peptide levels, so then it's okay, we can just apply the test between two years, such as t-test between two groups. But if you want to analyze at protein level, then we have to summarize the protein to a, so using suppose there are 6 peptides corresponding to a protein, then we have to take suppose mean value or something like that. So we have to summarize that. And after that, we have to normalize the data so that accounts within variability and between sample variability. So there are various methods for normalizing the data, such as quantile normalization. Then another method is SVD method, that is called singular value decomposition method. So this is a general workflow of a level-free quantitative data analysis. So after the experiment is conducted, we get the data as earlier shown in the Excel sheet, like peptide. So that are the peptide intensities. And in the first step, we first perform the pre-processing. So we are summarizing to the peptide level intensities to the protein level using methods such as mean or median or sum. And after that, we normalize the data. So if you want to analyze we have to normalize the data, and we have to fill up the missing values. So we have to, or otherwise we can ignore it also. So in that case, we can use the method such as called unbalanced ANOVA, or we can use some imputation methods. Then after imputing, getting the complete data, we can simply apply a. So there are various tests available. For 2 groups, it is like t-test. There 2 or more than 2 groups, it is ANOVA, fixed or mixed effect models. So there may be various model. Suppose there can be extra covariates also, such as in case of human, there may be extra like age factor, height. So these are the other fixed effects. So in that case, we can use linear mixed model. And so this is for the protein level analysis. And if you want to do analysis at peptide level, then it is straightforward. Just we have to normalize the data, then we have to impute the missing values. Then we can use different methods such as linear model with peptide effects. So these are the basic workflow. And so here some of normalization given here, such as various stabilizing normalization, quantile normalization, median normalization, the eigenMS and local regression normalization. These are some of the methods. And I'm also, so these are some methods, imputation methods. So basically 3. So first method is the imputation by a single, is based on the local similarity based methods, imputation methods. And third is the global structure based. So in the imputation by a single value, so we are taking the half of global minimum intensity among peptides. So we are taking the minimal observed intensity among all the peptides. Another is half of minimal intensity of individual peptide. And third is the random tail imputation. So we are imputing by a single value. And the other method is based on local similarity, the KNN method, and the local least square method, and REM, that is called regularized expectation maximizer algorithms. So these are the methods based on local similarity. And there are two other methods based on the global structure, that is called probabilistic principal component analysis method, and another is Bayesian PCA algorithm. So these are the imputation methods used. And so there are various online resources for storing the raw data, or submitting the raw data, and from that we can also analyze the data online. So these are some of the data, online resources such as PRIDE, Peptide Atlas, iProx, Tranche, and GPMDB. So, and in proteomics data, we are getting the data format in the form of raw data. Means it is in like CDF format or MGF. And these are some of the, so there is some software called Mascot. So like MGF is from that. So, and from that we have, so there are various software from which we can obtain the expression data. So, and so now the topic is differential expression analysis. So this is generally carried out for detecting the significant differences of between two or more than two conditions. And in this approach, in this analysis, we first normalize the data. So we can use the transformation and normalization techniques, such as like we use the log-based 2 transformation. Another method is quantile normalization. So in quantile, we are using the log transform data and then we are using the quantile method. And the third is the variance stabilizing normalization. So it is directly applied. It is applied to the raw data. Another is median scaling normalization. So we can apply any of these methods. And in case of missing values, so we have to impute the data. So most of these methods are, so there are various methods like such as SVD method. So in most of the situations, SVD is used, and besides this, there are another method like k-nearest KNN method and MLE method. So these are some of the methods for imputing the data. And there are various statistical approaches or tests for carrying out the differential abundance or expression analysis, such as t-test, moderated t-test, ANOVA, linear mixed model, and there are various tools and packages available. So, such as DATE-R. So DATE-R, MS stats. So these are written in R. And similarly, we have Panda View and Panda. So these are online softwares the user can do online. They have also provided the standalone application. Then MSQ-ROB, and another is Rep Explorer. So that is also online. So that DATE-R, that is a comprehensive package of R, and which can perform statistical and diagnostic function for the quantitative proteomics data analysis. And in these various steps, such as normalization, imputation, testing of hypotheses, all these are included in these packages. And here, imputation is based on, so for imputing the missing values, random selection based on censoring probability from ANOVA models parameters. So this is the method. This method has been used for imputing the missing value. Another is this is called this is an R package developed by the Choi et al. Group, Choi and others. So it can perform the analysis for label-free as well as label-based experimental workflows. and data dependent targeted and data independent spectral acquisition. So it can support most of the types of most of the proteomics experiment, which can be level free or level based. And here the expression analysis is based on the linear mixed models in this package. And another is Pada view. So it is the user-friendly tool for analyzing and visualizing the proteomics data, and it has various methods, analysis steps, methods such as normalization, imputation of missing values, statistical test, clustering, and PC analysis, and the interactive volcano plot. So, and this is another Miss Panda. So that is also for proteomics data quantification. So this is MSQ of that. This is an open source R package. So it is available as online as well as package. So the code is available online, and it also provide there is a tutorial present on the GitHub side for analyzing the quantitative proteomics data. So it mainly deals with the level free MS based quantitative proteomics data. And this is another, this is online tool. So this is a web server, Rep Explorer. So from that we can analyze the proteomics as well as metabolism data, having the biological and technical replicates. So in that, so there are two methods available for normalization, that is median scaling and VSN method. And the test is based and the statistical test is the empirical based moderated T statistics. So this is the test. So instead of T test, we are using empirical based moderated T statistics. So this is an example given in REPS. So this is simple, means the first column is the biomolecules or the peptides or proteins, and these are the. So there are two groups, control and the case, and within each group, so there are two biological replicates having two technical replicates, like control underscore is replicate number 1, and then so the second and third column is it corresponds to the biological replicate, that is the technical replicate 1 and 2. Similarly, control 2.1 and control 2.2. These are the technical replicates corresponding to biological replicate 2. Similarly, for other, in case of case group. So here, so I will show you means online. So this software and another software developed by me. So this is the screenshot of the software. So here, okay. Otherwise, I will show you. So these are the various options available, like we apply the variance stabilizing, normalization, median scaling. So these are the two methods available. And after running, so first we have to upload the data, or either we can use example data set for demonstration. Then we have to use some normalization methods. So in this web servers, the method for imputing the data, imputing the missing value is not given. So the user has to submit the imputed data, the complete data set. Then after running the tool, so there will be 4 tabs. So in the first, it will be the ranking of biomolecules. Second will be the heat map, and the third will be for downloading the ranking table. And okay, these are the result. And this is the ranking table of differentially expressed features. So the first column is the biomolecule identifier. Second is the log fold change, and another are the probability of positive likelihood ratio. So this is the test there. And the last 2 columns is the adjusted p-value. So and this, one is the E-based p-value and another is E-based adjusted p-value. So if we have a large number of, so if you apply any test for a single protein or peptide, it will give only the p-value, but we have to make correction. So that will adjust the multiple multiple protein or peptides. So if there are 10,000 peptides or protein present, then we have to adjust the p-values. So there are various methods for adjusting p-values, such as means like Bonferroni method, then Benjamin-Hochberg method, BH method, FDR method. These are some of the methods. And here in this table, second column is the log fold chain. So it is 1.666, means it means 2 raised to the power 1.6. So in the first group, so this biomolecule 90, so it is almost 2 to the power 1.66 times, means more abundant as compared to the reference group. So this is the example, like for biomolecule 36. So if you see here, it is like minus 0.8. So blue ones is down regulated as compared to the red ones. So the case is down regulated. So the proteins in the case is down regulated as compared to the control. So this is an example of upload. So now I will. So these are some of the references, and then I will show the online tools. So these are the references. So there is some.
Hello.
Hello.
Dr. Can you hear me?
So I'm giving some demonstration of the online tools.
Please, sir. Go ahead, sir. Please go ahead.
So actually, it is not showing. So otherwise, I will show my own software.
Yeah. So better you have to show your own software, and whatever the data you have to upload, accordingly you have to share your screen, sir.
Okay. So is it? Can you see it?
Yes, we can see it.
So this is the software developed by me. So this is the home page. Another is demonstration, and third is the online tool. So here this is the home page. So from that the user can have basic knowledge about the software, and this is the demonstration how to use this tool. So I have named this tool as Statistical Analysis Tool for Proteomics, that is SATP. And here you can also download the supplementary files for demonstration. So supplementary file 2, suppose you can download this data also, save this data, or another is supplementary file 3. So supplementary file 2 is the intensity data, and supplementary file 3 is the additional information file. And here all the how to what should be the format of the data, and what are the how to use the software, all are given. So I will show you with examples. So in this software, first I have to browse the file. So I have already downloaded the file. So just I have to browse the file. So I am uploading this file. So that is in Excel sheet. So after, so it will come. So it will show at what level you want to analyze the data. Is it at protein level or at peptide level? So can you see this?
Yes, sir.
Okay. So suppose I selected at protein, I want to analyze the data at protein levels. And how to aggregate this, like mean, median, sum, or maximum value. So for each protein, there can be various peptides. So how to aggregate the intensity data? So just I'm selecting the mean. Another is the additional information. So if you see here in demonstration, there is a file. So that is the file, that is the additional. So there is Excel sheet containing this additional information. So there are total 18 samples having 3 groups. The first 6 samples belongs to control, then S7 to S12 belong to case 1, and S10 to S18 is case 2. And there are other covariates such as gender, race, and age. So gender and race are categorical fixed effect. So gender can be male or female, and race can be white or black. So these are and another is the age, that is the continuous variable. So age in years. And there is a column called bio and run. Bio is the biological replicate number 1, 2, 3. And run is so we can perform the experiment in 2 runs. So run 1 and run 2. So there are 2 runs. So this is this file I will upload here. So this is another file. So after uploading file, so I have to use the categorical fixed effect. So suppose I want to include the group also. Suppose I want to include gender also. I'm interested in gender also, and I'm skipping others. So like group, gender, race, these are the fixed effect, categorical fixed effect. So I'm choosing group and gender. And another is continuous fixed effect. So here only the age is the continuous. So I will select age. Then another is a random effect. So suppose we are conducting experiment on different days or different run. So that are considered as random effect, having the random effects. So here the run will be in the random effect, the variable having the random effect. After that, so we have here we have chosen categorical fixed as group and gender. So here, so at what level you want to analyze, according to group or according to the gender? So I'll analyze according to 2 groups, case or control 1, case 1 or control, or case 2 or control. So there were 3 groups, control 1 and case 2. So automatically it will come all the comparisons, control versus case 1, control versus case 2, case 1 versus case 2, case 2 versus case 1. So all the combination will come, all the pairwise combination. And here we can analyze the data after remove the features having the missing values. This is one method. And another method is if you don't want to ignore the missing values, we can impute that. So another method is imputing missing values. So in this I have included 2 methods. That is the singular value decomposition method and the k-nearest neighbor method. So these are the 2 methods. So here I am choosing the SVD method. Now we have to normalize the task. So we can simply do the log-based 2 transformation, or we can use other method, that is log-based followed by quantile normalization. So here I am using we can use any method, but in many cases the experimenter may have the normalized data, already normalized data from their software. So they can choose none in that case. If they don't have the normalized data, they can use any methods, log2 or quantile. And here, so first, and now we have to choose the appropriate method for testing. So first is the lemma-based method or the moderated t-test method. So this is the most important method. So in most of the papers, this method is used. Another method is based on the linear mixed effect model. And third method is t-test. So if you have two groups and we want to compare two groups, just we have to click on the t-test. And so there are different forms of t-test, such as equal variances t-test. Then another test is called Welch t-test. So the groups are having unequal variances. Another is the pair t-test. So based on the experiment, the user can select any type of t-test. So here I will use just the simple moderated t-test based method. And this is we can specify the significance level. Like so alpha, that is the value can be 5% or 1%. So by default, it is giving 0.05%. And another is the log fold chain. So what should be the log fold chain? So like if the log fold chain is 1, it means that suppose in group 1 and there are two groups, group 1 and group 2. So if in group 1 the intensity is 1000 and in group 2 it is 2000 after taking log. So log value is 1000 and log value is 2000 in another. Not log value, suppose it is like what we call, suppose after taking log there is 1 in the first group and 2 in the second group. So if you take the fold chain like 2 by 1, so means if you take it is like 2 raised to the power 1. So if you take the difference, it will be like 2 minus 1. It will be 1. So means it is double expressed as compared to the first group. And these are the various methods for adjusting the multiple proteins, multiple feature testing. So by default, that is the Benjamin Hochberg method, and so it is less stringent method. And another is Bonferroni method, so it is tight method. So besides this, there are other methods available, that is Holm, Hochberg, Hommel, and BY. So BH is a moderate method. So we have moderate method for adjusting the p-values. So if we submit the data, so after specifying all the parameters, just we have to submit and wait for the result. So now here, so there are various tabs. From here we can see what inputs we have selected. Like the first column is the input parameters and second is the input selected. So like the feature type. So we have done analysis at protein level, then aggregation method. So we have used mean. So and there were two categorical fixed effects variable, that is group and gender. And age was the continuous fixed effect, and run is the random effect. And here we have compared control versus case 1, and we have used the SVD method for imputing the missing values, and we have used the quantile normalization method, and these are all the input parameters. And in the second tab, so we will see the box plot for each of the groups. So like in the first box plot, so it is for control group. So there are 6 samples, S1 to S6. So after taking the log 2 and taking the quantile normalization, so the plot will be like this box plot for the control. So and in the second plot is for the case 1 for the samples S7 to S12, and there is another group case 2 S13 to S18, and this is another plot, that is density plot. So if we can see that the data is so after normalizing the data, it is approximately normal. So just for normalizing the data, it is in all the 3 groups it is almost normal. And this is the correlation heat map. So this is interactive map. Like suppose I want to suppose here S2 and S1. What is the correlation? So it is 0.46, and the p-value. So similarly, we can see the correlation between any two samples. So it is interactive plot. And if you see, there is so we have I have provided all the download links. So like in boxplot, we can download the boxplot image. Suppose the user want to just, so I'm downloading. So if all are downloaded, the box, we can download the plots also. You can download the density plots and the correlation heat maps. And this is the multi-dimensional scaling plot. So that will show how the samples are clustered together. So here in control, so these are the pink ones, and the case one are the green ones. So only one green, it is like outlier, means it is, and this sample is not good. So we can discard this sample. Like you can see the sample number as 12. So it is not with the group of green colored. So it should be in the same group. From that, here we can check the quality of the samples also. So blue is okay, almost okay, and red is almost okay. But in green, one sample is means very far away from the group of the case one. So it can be used for the quality check. And this is the summary of the analysis. So in this data, so we have total 200 proteins. Actually, in this data, there were 1,000 peptides correspond, and for these peptides, so there were only 100 proteins. So we have total number of proteins is 200, and the total number of differentially expressed proteins is 70. And the third row, it shows the number of differentially expressed proteins between the -1 to 1 log fold chain. So it is 33, and the third row is, it shows how many are upregulated. That is, the log fold chain is greater than equal to 1. Hello. So it is only 16, and the number of down-regulated proteins, it is 21. So this is the summary. And this is the protein. This is the ranking table. So if you see the first row, it is protein 1, and it has only one peptide in this protein. And we are also showing the missing value percentage in control and case. So in control, 16% is missing. So out of 3 samples, it may be is 3 out of none. So I have to see 6 samples. 6 samples are, and so I think 1 is missing. And in case 1, 33% is missing. Like two observations are missing. And the log fold is minus 0.68. And so this is the T, the moderated T, and so it has the degree of freedom 13, and this is the p value and adjusted p value. Similarly for row 2, so there is this is the protein number 10, and it has 10 peptides. And we can also sort the table according to the adjusted p value. So if you see, so like protein 163, so we are taking the cutoff of 0.05. If the adjusted p value is like less than like 0.001 or 0.005, we will consider it as significant. So here protein 163 is significant. So here the log fold chain is 1. So it is double times, that is 2 raised to the power 1. Similarly, it is protein number 52 it is also highly significant. So this is the table of differentially expressed features, and this is the yeah, this is an interactive volcano plot. So that is the plot means, this means the plot in that axis is a log 2 fold chain, and in y-axis we are taking the minus negative value of log 10 p value. So we are taking the log base 10 of p value, and then we are taking the negative of that. So this is an interactive plot. So and there are two orange lines vertical. So these are the cutoff of fold chain. So it is like -1, yeah, 1 and -1. So we have set that value. So below, so blue one are the down regulated. So the blue dots are the down regulated proteins or features. If we hover around the, suppose I want to see what is the, so it is here, it shows the log 2 fold FC minus 0.42, and the minus log 10 p value is 4.18, and the status is down regulated, and this is for the protein number 83, and it has 3 peptides. Similarly, in red ones, it is log fold chain is 1.97, so it is greater than 1, so it is up regulated, and it is the protein number 111. So you can see that, and these are the, and the green ones are between the cutoff value of the log fold chain. So this is for, so this dot is corresponds to one protein 154, and the black ones are the non-significant. So these are not significant. So this is, so this volcano plot is made using the p value without any adjustment. So similarly, after, so for correcting the multiple testing problem, so after adjusting the p values, we will get this plot. So we can see the status after hovering around the, so here same is there. So blue dots are the down regulated, and the red ones are the up regulated, and the green are the between the +1 to -1, and the black ones are the non-significant. So this analysis was based on protein level. So we can also change, suppose we want, so here, so the analysis was at protein level, and we can also download the data. So if you download the data, we will get all the, suppose, so this is the data. So I will open, so this will give the result. Are you able to see the Excel sheet?
Yes, sir.
So it will give the result. We can download the result also. Like, so we can see the result. So this is for the 2 groups, and it also give the result for all the 3 groups together. So if your data having multiple groups, so it will give the complete result. Like, so it will give for all the 3 groups. So what is the percentage of missing values in group 1, group 2, and it uses the F statistic. So what is the F statistic and the p value, and it will give all the pairwise comparison. So it is the overall result. And here this is the normalized data. So the user can download this data. So this is for the protein level. Protein level. We can also, suppose we want to change that peptide level. So just we have to submit it again. So the rest parameters are same. So after that, so here we can see now the peptide is changed. So the feature type has been changed, peptide now here. And here the summary. So I'm clicking the summary tab now. So there number of peptides becomes 1000 here now. So number of proteins were 100, and here now we are doing the analysis at peptide level. And out of 1000 peptides, 282 are differentially expressed, and in 282, 88 are up regulated, and 121 are down regulated, and rest are between the cutoff values plus or minus 1. So, and if you see here, we will get different tables. So we are getting like peptide level. See, suppose this is the peptide, and we are getting the analysis of peptide level only. And like second row, it corresponds to protein 10. Third also corresponds to protein 10. Fourth, fifth, all corresponds to protein 10. So this analysis is based on the peptide level, because most of the many experiments are interested in peptide analysis. So and we can also see the other data like by clicking on the respective tabs, and we can adjust the p-values. So we can sort the table according to the adjusted p-value. So these like proteins 130, 196, these are highly significant. Similarly, we can see the volcano plot. So we can see the status. So do you have any questions about this software? Hello? Hello?
Yes, sir. Yes, sir. Are you going to finish this lecture? Yes.
Yeah, so I'm going.
Yes. So we have requested to send a question in chat, but nobody has sent any question in chat. So thank you very much for giving this lecture.
So this is the reference.
And I would like to know from you whether your team or you have hired some agency and you have developed this software, or within your institute some persons are there?
No, I have developed by oneself. So I have implemented all the codes in the R. So there is a package called R. So in that I have written all the codes in R. So and there is a package called Shiny for making the web application. So I have used that web application. So after making the web application, I have hosted this on there is a server called Shiny Apps. So that is a free server. So I hosted that server, my software on that server. So, and this was my PhD work.
Good.
And
yes, that is.
The paper is under revision. So I have submitted.
Okay, paper is also coming. Yes.
Paper
in
will
which
come.
Journal it is coming, sir?
Yes, it is a review. So it is in PLOS One submitted. So they have given me the comments. So I have to revise the
rectify that comments. Yes.
After revision, then I will check whether they will submit accept or not. So there were two reviewers. So one is okay with one is okay with me software. For another reviewer I have to incorporate his suggestions. So I think so in that case the software will be more powerful. So it will be more useful.
Yes, and in future also you might be incorporating some more facilities in this software. We hope and wish you all the best for that thing.
I have taken a project here, so in that project, so I have taken the project. So in which,
so, sir, are you going to put this software in our IASRI's website?
Not this now, but it is the link is given here. Now you can see you can open from anywhere from your laptop.
It's a freeware, sir.
Yes.
It's a free
good.
Open domain.
It is. Okay. I have done.
Please, Alok, take over. Yes.
So this is open. So you can note the URL. You can open this also. But it is not still. It is still under. The publication is still under progress. So I think it will take 3 to 4 months.
I do understand, Dr. Sudhir, and very excellent and fantastic work that you have performed. I know most of the people are in fact not aware what kind of most of the fraternities belongs to statistics. So I know as when this is interdisciplinary things are there, when we upgrade and so then the things will be somewhat different. So it is really excellent work, and I think some little bit presentation is still left. So please complete it, then we will discuss. Please, sir.
Actually, just it was thank you slide for that. That's what.
Okay, okay. So I request.
Actually, this is my email contact, email ID. So if any query, they can send me the request, or they can email me. So these are 2 email IDs. So the participants can note down my email ID and they can contact me if they have any query.
Okay, sir. One query is there. How it is different from BLAST and FAST?
BLAST is like, in BLAST we are, so there is on NCBI there is a BLAST. So we are just submitting the sequence and it will search the sequence. So there are various sequences already submitted. So there are databases. Okay. And in that it will search which is the most closely related, and they will give you the most closely related sequences corresponding to your input sequence.
Okay. And what about this software, sir?
So this is for the analysis. So if you have some expression data of proteomics, just you have to put that data in that format according to my format, and you have to upload this, and you have to just specify the various input parameters, and you have to submit the button.
Okay.
And it is very fast, so we will get result within like 10 seconds.
Sir. We have already operated BLAST and FASTA, and we have seen what kind of speed and what kind of difference is there. So like Chaturala sir asked one question regarding, sir, whether it is available in open domain. Is it so?
Yes, I have just.
Yes, sir.
It is not
available in open domain, sir.
Actually, I have not. See, it is open domain. You can see this na URL. There is a URL called ulbbf.sinef.io.
Okay.
So you can note down this URL. Okay. And otherwise, it will come in my annual report this year. So in ISRI annual report, I provided the link in my report.
That is why, sir, actually, Dr. Chaturala sir is asking whether it is available in ISRI software or on homepage. It was a great achievement. That is why we are interested.
So you can note down the URL. It is free.
Okay, sir. Okay.
And in the meantime, if the paper is published, then you can use the R codes also.
Okay, sir.
From here, you can only analyze your data, but you cannot see the R codes.
Okay.
So after publishing the paper, I will make available the R codes available to all the users. And if our annual report will be released this year, you can see the URL. I have provided this also in the annual report of ISRI.
Okay, sir. Okay. So thank you for a wonderful presentation. In fact, innovative presentation as far as my concern. And now I request Dr. Nitin for the same. Sir, can you stop and share? Can you stop your presentation, please, sir?
Okay, I'm stopping her. Is it stopping her?
Please stop, sir.
Okay. Hello. I'm audible, sir?
Yes, Nitin.
Yes, thank you very much for such nice, very nice presentation, sir. You very well discussed about the problems in proteomics data, like missing value in the sample, and told about the percentage of missing value and heterogeneity of data and classification of various kind of missing values and the imputations method. Sir told about the step-by-step analysis of proteomics data. Lastly, he demonstrated some tools about the analysis of data. He developed a very informative, easily handle software that is statistical analysis tool for proteomics. He very well demonstrated with the peptide kind of data and the protein level data. And with that, with the second, you can get the out peptide data or protein level data. Thank you very much, sir. From our organizing team, we are just showing these certificates to you as a token of love. Thank you very much, sir.
Thank you.
Thank you very much, sir.
Thank you. Thank you, every participants and Dr. Alok Srivastava.
Thank you, doctor. Thank you.
Thank you, sir.
Before moving to the next session, I would like to request Dr. Nitin as our next speaker is there, Dr. D. Bhattacharya, sir. He is Dean and Professor in Head in Vishwabharati University. So I request, so please give some brief about him.
Okay, so I'm leaving now. Okay.
Okay, sir. Thank you, sir.
Thank you, everybody. Thank you.
Thank you.
Okay, sir. So we have a very nice presentation by Sudhir Srivastav, sir. Now we as moving ahead in our session and 2 days webinar with this last lecture of Dr. D. Bhattacharya, sir. He is a Dean, Professor and Head of School of Science, Vishwabharati University, Kolkata. He did his PhD. Did his PhD from University of Calcutta. Dr. Bhattacharya is visiting professor of the Department of Statistics, University of California, USA since 1998. His research interest encompasses statistical inference and for dependent process, contiguity, reliability, engineering, etc. Sir has created a significant number of research papers published in national as well as international journals. He authored a number of books in statistics, probability, and statistical inference. Now he will deliver his lecture on a very important talk that is very informative for the agriculture background, scientist, assistant professor, student, that right statistical technique for the right situation, that is stats of significance. So over to you, sir. I welcome you to this seminar. Welcome, sir.
First, I would like to thank the organizer for inviting me to talk before you. And especially, I would like to thank Alok for contacting me and requesting me to deliver a talk. Basically, what I have prepared is for the students, because teachers are not making many mistakes. So what are the errors students are doing that I will point out in my talk, and how to handle those situations. That will be the focus of my talk. Am I audible?
Yes, sir. Yes, sir. Please.
Yes, sir. Yes, sir.
Okay. So let me share the screen with the can you see the slide?
Sir, that slide show. Click on that slide so that then.
I'm not getting that one here. I am getting view and then.
Sir, press F5. So directly press the F5 button of the keyboard.
It's not coming.
Click on presentation first and then. Sir, enter first. First enter. I think it's not click. It is showing the viewer. View only of the file.
Sir, double click the selected file, it will open.
Yes.
Double click.
Now can
Yes, it is opening.
okay, okay.
And after that, you can use F5 key or slideshow.
Okay, so this will be the title of my talk, the critical analysis of data to take right decision. And this is the abstract. Now, you can see that every day we are collecting data to get something, to do something and to take a decision about something. So, but before getting into the decision, before going to make some conclusion, we need to have a better understanding about the data. So to make sense of the data and to take right decision using the data, information contained in the data has to be extracted. And for that, you must have some good ability or understanding of the data. So what kind of understanding we need? We need about the types of data, the process of obtaining the data, how the observations, how the data have been collected, and then different exploratory data analysis tools and techniques, whatever you have, inferential tools and techniques, whatever you can apply in that context. So all these things you must be aware of, you must have a good understanding on that, and then you can get a good decision from your data. Now, to do that, let us so this is the first slide. Basically, you can see this is a very basic matter that under what conditions you are collecting data. That is, there are different kind of data. As I mentioned, that the agriculture department collects the information on yields of crops, amount of inputs used. Meteorological department measures and collects data related to weather conditions. So these are the issues where some issues I mentioned, but there are various issues where from you can get the data. And the purpose is to make an optimum decision based on the information collected. And so these are the steps actually we need to follow. First, we have to identify what is the problem. The second step should be that before processing, before starting analyzing the data,
Excuse me, sir.
Yes.
Sorry to interrupt you, sir. Actually, presentation is not visible. Only file picture, whatever the file, whatever the picture inside the file, that is depicted. So my humble request, please close the presentation, sir. And once again, open the file where your file is located. So first, please, yes, sir.
Okay.
Stop the presentation first, sir.
Okay, I stop it.
So then again, share your screen. And where actually your file is located, just go there. Go to that place, sir. So this one, sir, so it is there, sir, on side, above, sir. Lecture Bharuch, it is there, sir. Yes, sir. So wait, sir. Sir, just right click, sir. Right, the file, sir. Right click here. Right click, sir.
Yes.
And open, sir. It will work, sir. It will work, please. Okay, sir.
Is that okay?
Yes, sir. Now press F5, sir.
It's not working, I think, F5.
Sir, F5. Then, sir, it is bottom side. The presentation option there. See, sir, one cup-like structure is there. Top right bottom is there, sir. Right bottom, sir. Right bottom, sir. Yeah, it is there, sir. Now it is visible, sir. Thank you, sir. Thank you. I'm sorry to disturb you, sir. Sorry.
No, sorry. So we were at this page. So these are the necessary steps to make any decision, to analyze the data and to make any decision. One is that we have to first define what is our problem. And on the basis of the problem definition, that means on the basis of your objective, you have to collect data. And then you collect data. After collecting data, you have to have a preparation of the data. And then when your data are prepared for analysis, then you use some tools and techniques to get the results and then apply the results in the particular situation. So the problem definition is the first and very important step in any data analysis technique. Here if we do not have clear understanding on what we want to conclude, on what is our objective, then you cannot select the appropriate tools and you will be misleading in some place. Now, data preparation is also very important because there may be bad data points, and that bad data points you have to identify, and you have to eliminate. Without eliminating the bad data points, if you perform analysis, then your conclusion may not be right. You will get a different conclusion. So these bad data points can be in different form. It can be bad. It can be a true data value but an outlier. It can be a mistake. It can be typos. It can be measurement error. So in many different forms, a bad data point can appear. So, but you have to identify if there is any bad data point in your data set, and you have to eliminate those bad data points before putting data into analysis. So that is a basic requirement of analyzing and getting conclusion from the data. And now, what are the ways you can make use of for collecting data? Now you can find that there are different ways: direct observation, designed experiment, and survey. And direct observation, as we know, that we just reach the unit and take the measurement as they appear in nature. So just go there and take the measurement. In another type of collecting data, we make some experiment, wait for some times, and then when the result is available, we get the data, and then we analyze. And in survey method, we do it by sending some questionnaires or preparing direct interview by using a schedule kind of thing. So these are the three ways you can collect data. These are collecting the data we are talking about. And always there is a scope of compiling the data from secondary source. So here mistakes can happen, error can happen. That has to be also taken care of. Otherwise there is a problem. Because suppose in survey method, basically the social scientists, they're using the survey method where they used to send a questionnaire and to the respondent. When respondents are not replying back or sending back the questionnaire for different reasons, and for that some non-response is appearing. And because of non-response, you are not getting good data. So how to reduce the non-response, how to reduce that kind of error, that is an interesting part. What I can suggest is that you can run the questionnaire in a small group, which you can call as a pilot run. Sorry. And then using the pilot run, you can estimate that what is the time required to fill in the questionnaire and get given average time to fill in the questionnaire and put that estimated value at the bottom of the questionnaire. This is called estimated time burden. So if you mention the estimated time burden, that means when the respondent will get it, he will know that, yes, I will have to spend 10 minutes. So, okay, I will fill it and I will send it back. But if you do not mention it, then, and maybe a 10-page or 20-page questionnaire, then then the respondent may think that, okay, I will answer it later on. But that time will not come again. So he will not return it and you are not getting the data. So this kind of error can be reduced by just mentioning the estimated time burden. So you run the questionnaire in a small group and get an time estimate, average time estimate to fill in the questionnaire. And then you mention that. Another very easy method, another way of reducing this, there are different components of different ways of reducing non-response in different non-response arising out of different reasons. And another one can be done by sending a self-addressed stamped envelope, because while I can see, a respondent can see that yes, a stamped envelope is there, so he don't have to go to post office and post it, and he don't have to pay some money to post it, so he may do it. So there is a little reduction in the non-response. So in survey method, reduction of non-response is a very critical issue, and that has to be, an error is introduced due to the non-response, heavy non-response. And also in case of direct interview method, there is a question of substitution. And because of the substitution, also the error are introduced. Now, when you are collecting data, whatever the method, direct observation or design of experiment, whatever the method or survey method, you have to select the respondents in a very random manner. That is a very basic condition. And if you do not have a randomly selected respondent groups, then your conclusion cannot be generalized. Your conclusion cannot be generalized. That is another thing. So from the data part of view, you have to take care of the mistakes. There can be some measurements error that I will talk later on. But at this point of time, you have to take care of non-response, error due to substitution, and okay, so now again, these are very basic things, but why I am introducing this basic thing is because if you do not know what kind of data sets you are handling, you will be in a dilemma of using what kind of statistical tools and techniques you will use. Not all tools can be used in all data sets. So you have to have a good understanding about your types of data. That is very important. That is ordinal, non-ordinal, discrete, continuous. So these are basically for the beginners, they must know that how to what is the data type, the classifications. Okay, so now I will give an example where some caution or some error can be made, but let us see that case study. Now here is an example. Suppose I am studying the survival rate of smokers and non-smokers, and this is the data given. Among the smokers survived 443 number of persons and 582 are at risk, and among the non-smokers survived 502 number of persons and at risk 732. So now the question is that who is at more risk, the smoker or non-smoker? That was the objective of the study. So when we find this data, we analyze it, and then we find the survival percentage for the smoker group and the non-smoker group. So we find that for the survival percentage for the smoker group is 43.2, and survival percentage for the non-smoker group is 40.68. So it is observed that smoker group has more survival percentage. So does it seem to be usual? That was the question. Does it seem to be usual? Do you agree what we got? So here a critical study is needed. That was our idea, that it is not going in the right direction. But just by analyzing this data and finding the survival risk is not giving us the right answer. But the data, I have the data, but if you follow the direct rule, not the logic, then your answer is that non-smoker group has more survival percentage. So now we made a critical study. So we went back to the original data, and then we find that the data was a part of a big data. What was that? The data actually was collected on the basis of age group. So that was the data. Age group 18-25, 25-35, 35-45. These are the age groups, and survived for both non-smoker and smoker. So now we got the full picture. So now we calculated the percentage, survival percentage. You can find here 49.07, 49.38, 46.58. So this is the survival percentage for each group. And here the survival percentage for non-smoker, these are the survival percentage. Now, if we compare for each group, then we can see that non-smoker has more survival percentage in most of the cases. Only one case, I can see that this age group, 25-35, smoker group has more survival percentage, but otherwise, more or less, non-smoker group are having more survival percentage. So that means here we are going in the right direction. So what is happening here? Happening is that we are combining different groups of observation in a single group. So when this kind of thing is done, then there is a variable which remains confounded in the final data. That variable is playing the role. That variable is very important. It's called the lurking variable. That variable is very important. Now, if we combine such kind of different tables, different groups, then our conclusion may be reversed. So which is not actually the way we conclude. The conclusion should be different, but we are getting a different one. We are getting the conclusion not in the right direction. So this is happening because we are confounding a variable. We are not reporting the variable in the final table. That happened here. That happened in this table. Here we are not reporting that this survived and at risk, this number of observations are calculated. There is an age group for different age group, not for the single age group. There are different age groups and they are added, and that addition is giving me this number 443,582,502,732. So that means if we split the data, the final data, in according to the variation in the lurking variable, according to the group of the lurking variables, according to the category of the lurking variables, then we can get a better result. So we have to be cautious about that that kind of data set. Okay. So age is playing a very crucial role. That has to be. Now again, here is another case study. What we find interesting is that now in a city there are two hospitals. One is a large hospital and one is a small hospital. Now the patient died and the patient survived for both the hospitals are given. 90, 2110, small hospital 23, and patient survived is 677. Total is this. Now, the question was that it was needed to take a decision. One student got ill, and the question comes that in which hospital he has to be taken. And so, with this data, what we would see that we will find out the survival percentage. So we find out the proportion died and proportion survived for the large hospital and the small hospital. So you see the proportion died in large hospital is 0.04 and proportion died in small hospital is 0.03. Proportion survived is here also it is something more. So I can see that if I consider this conclusion, the proportion died since it is large in large hospital, so I should not send the student there. I should send him to the small hospital for admission. But I think this is not a very reasonable conclusion. So here also it needs a critical study. So we found that when we went back to the data source and we found that there are cases of sickness which are not equally serious. Some cases are more serious, some cases are not so serious. So, so basically in large hospital, more serious cases are going there. And since more serious cases are going there, so the data, they are getting more death. So that may be the reason. So let us see what is happening. We divide the data in terms of serious and not so serious cases. So you see here the not so serious patients, serious patients. So it has been divided. And then so then we find that according to the seriousness of the cases, we find the proportion of death and in the small hospital and in the large hospital. You can find here that the proportion of survived and proportion of death for the large hospital, proportion of death is less, proportion of survived is more. In both the cases, not so serious, serious. In both the cases, we can find out that the proportion survived is more in large hospital. So now you can conclude that your patient should be recommended for the large hospital. Basically, this was not a very good decision that to send a seriously sick patient to a small hospital. So that was the idea. We started the critical thinking, and we found that yes, there is a problem, that serious cases are more going to large hospital and there is more death. And because of that, the percentage is dominating. The percentage in the combined table is dominating. So now if we separate this out in the classification of not so serious and serious conditions of the patients, then we can get a better decision. Okay. So here also, what is the variable confounded? The variable remains confounded is the seriousness of the patient, the conditions of the patients. That is a variable which varies from patient to patient, that was not reported in the combined table, in the final table. So you see that if the first table is used as an advertisement, suppose the small hospital is advertising in the way using the first table, you cannot sue them, you cannot make any case against them, because this is a real data, right? This is a real data. So you cannot make a case against them, but you will be misleading. You will see that small hospital is good. They are making an advertisement that our hospital is good, though small, but it is good. But really, it is not true. So we have to think critically while taking a decision. These are all parts of exploratory data analysis, and you must have a good understanding about the data, what kind of data you have, what are the types of data you are handling, and in what way you have collected data. Basically, the way that the data represents the population or not. Those kind of things you have to be, and also you have to eliminate bad data points. Okay. Now this will be my third example, and we'll go to the next part of the talk. This is also an interesting example. Now a study was conducted to see that the time spent in watching television program in hours per week, whether that affects the academic performance of the students as reflected in GPA. So that was the point of study. So it is a data. Now, how many hours they spent per week, and finally what was their GPA. Now, after getting this data, it was analyzed that the just simple correlation, Spearman's correlation between the number of hours per week watching television and their GPA. Now it was calculated and it was minus 0.02, which is very negligible, almost zero. That means what should be your conclusion? Your conclusion is that there is no impact of watching television and the academic performance. But that should not be. That should not be. That is not a very reasonable conclusion. So, what should an analyst do at this point? Make a conclusion based on this result or go for further critical study? So definitely we need a further critical study. Now, it was studied that, it was observed that there are students who are, there are two different kinds of groups. One is that they are watching entertainment programs, sports, movies, those kind of things. And there is a particular group of students who are watching some educational programs. So we separate the students by asking them that what kind of program they watch. So we get this kind of thing. So this is group one who are watching entertainment program, and group two watching educational program. So that was the group, I think. Group 1 watched mostly the educational program, and group 2 consists of students who watch the entertainment program. Okay. So now we have the same data. The same data, we just split it according to the types of programs they are observing. So now we calculate the correlation, simple correlations. Remember, I am not going into the higher order statistics because as I was told that I have to talk about the common error that we generally make. Basically, I prepared it for the students. Teachers are basically, they usually do not do this kind of thing. So we use simple correlation, just Pearson's correlation. Now, if I calculate Pearson correlation, then for the first group is 0.90, and for the second group it is 0.80. You see now, what is the reverse situation? High positive correlation for the group who is watching academic programs, and a high negative correlation who are watching the entertainment program. That means they are wasting their time. So since they are wasting their time not reading, so their GPA is negatively correlated. So that should be. So now we are in the right direction. So a separate analysis gives us a right picture. Now, okay, so I will stop for 2 minutes, and I will ask if there is any doubts, any questions up to this point. I can answer, and then I can proceed further.
No, sir, please go ahead, sir. Once the session is over, sir, so audience can ask in chat box. Please, sir.
Okay. How much time I have? 4:30?
Sir, yes, sir. Up to 30 minutes is there, sir.
4:30, right?
Yes, sir. Yes, sir.
Okay.
Okay, sir.
So now I will talk about the cleaning of data. Cleaning of data means I have to, whatever I said, that I have to eliminate the bad data points. Now, here comes the measurement error. Now, the amount by which each measurement differs from the true value is known as measurement error. So everything must have a true value, and when you are measuring, and if it differs from the true value, that is considered to be error, measurement error. And an error which consistently affects all measurements is called a systematic error. So here you can see that an error which is consistently affecting the all the measurements is called systematic error. Now, that can come through the through instrument. If you have a wrong instrument, if you are using a wrong instrument for measuring the thing, then you can have this kind of error. And this systematic error can make all the measurements too high or too low, right? And if you can identify this systematic error, then you can reduce it. Then you can take care of it. Then your data set will be good if you can identify the cause of this systematic error. So whatever systematic error, if you can identify them, then you can remove it. You can at least reduce it to some extent, to a greater extent. Now, there is another kind of error, which is a random error, which is an unpredictable errors in the measurement process. Okay. And the reason behind such kind of errors are not very clear. Since not very clear, so since you do not explain the reason, so there is very little thing to do about it. You have to bear with it. So this random error, you have to bear with it. Now we use a term, a bias. So bias is defined as a systematic prejudice in one direction. Error, we defined error. Now I am coming to the bias, which is a systematic prejudice in one direction. That means you are doing something over, you are doing something under. So this kind of thing, and that is done for all. Okay. So now, regarding the error, we will talk about the absolute error and relative error, because when we will try to identify the magnitude of error, then we can talk about the absolute error and relative error. The absolute error is defined as measured value minus the true value. That is the absolute error. And relative error is measured value minus true value divided by the true value into 100. So in both ways, we can reduce the absolute error or we can reduce the relative error. It depends on your situation, in which way you are comfortable with. And it is very natural that error decreases and accuracy of the measurements will increase. That is very natural. Now, what is the precision of the measurement? Precision of the measurement is defined as a deviation of different measurements from the center. That is the precision. That is all the measurements that will have a center, and if these data values are very close to that center, then it is more precise. And this precision doesn't guarantee you that it is error-free. So measurements can be centered outside far away from the true value. And all the measurements are clustered around that value. So your measurements are very precise, but they are not correct. Okay. So precision and error-free, these two may be different. Okay. So your measurements can be highly precise without being accurate. Right? So that also you have to take care of. That what is the actual thing happening in your case. Now, I have to eliminate, because I am under the data cleaning part. So I have talked about error. So I must be a little bit cautious about error, removing error, measurement error, and then I have to identify the outliers. So very simple technique I am mentioning here, but there are different tests also for detecting outliers. Now in a data set, you can find out, always you can find out the quartiles, the Q3 and Q1, first quartile and the third quartile, you can find out. And you can compute these two fences, Q1 minus 1.5 times IQR and Q3 plus 1.5 times IQR, and Q1 minus 3 times IQR and Q3 plus 3 times IQR. So always you can find out these two fences once you have Q1 and Q3. Now, any observation falling beyond this, Q1 minus beyond this fence, Q1 minus 1.5 IQR and Q3 plus 1.5 IQR is called suspect outlier. That means these data points which are lying here may create problem, may give you misleading result. Not necessarily will give you, but may give. And if some data points are lying here, outside this range, Q1 minus 3 IQR and Q3 plus 3 IQR, then definitely they will create problem. Your conclusion will not be good. So you have to eliminate these things. You have to eliminate those data points which are below Q1 minus 3 IQR, which are above Q3 plus 3 times IQR. Those data points are the bad data points. So you have to, so by this way you can find out the quartiles, find out the outliers, and you can remove the outliers. And in packages you can, if you draw a box plot, that also identify the outliers, and you can eliminate the outliers, and then you can after eliminating the outliers, then you proceed. Okay. Then your analysis should start. Okay. And another way of looking at the consistency in between the data points is that you can find out the data value minus the mean of the data value and divided by standard deviation of the data value, which is the z-scores. Now, if you find out these, if these data values are lying above 3 or below -3, then those can be viewed as outliers. This is another way of looking at the outliers. And you can understand that this basically, though we are handling with the sample observation, not we are considering the population distribution, but still, if you have a large number of observations, then definitely these scores will follow a normal distribution, a standard normal distribution. And then you know that the percentage of observations lying between -3 to 3 is 9.73%. So if any data points is not lying in between these, then definitely that is a bad data point, because the data point which is not coming within 99.73% of your average, that is not good. So that should be eliminated. So this is the way. In bivariate data also you can find, you have to, that in quartiles I talked about, that is univariate data, how to find the outliers. In bivariate data also you may have to eliminate outliers. And remember that in case of bivariate data, it is possible that for single variable there was no outlier, but in bivariate case it becomes an outlier. So that is also possible. Okay. We can find the multivariate data outliers in multivariate data. Now there we can use the Moholy-Nagy distance. This is the distance, actual Moholy-Nagy distance, x minus mu transpose, sigma inverse x minus mu, square root of that. Now, mu is the vector of mean value, sigma is the dispersion matrix of the data. Now, basically, this mu and sigma are unknown for the sample data. These are unknown. So it is better to estimate it. So this is the estimated Moholy-Nagy distance. X minus x bar transpose, S inverse, x minus x. So for any data value, we calculate this distance. And the estimated D value and the 97.5% quantile in the chi-square distribution, if D value is greater than Q 9.75 from a chi-square k degrees of freedom, depending on the what is the variable, how many dimensions you are considering, you can find out whether your data points, particular X, on the basis of which you are calculating this D, whether that is an outlier or not. So how far it is away from the center, which is the centroid here, how far it is away from the center. If it is at the reasonable distance, then no problem. But if it is more than this Q 9.75, then it is to be considered. Okay, so then there is another thing to be done before data preparation, that is data transformation. Sometimes you cannot apply your available statistical tools directly. You have to apply some transformation. Transformations are applied in for different reasons. Now, for first, for the purpose can be normalization purpose. That means you are comparing, you are having a data set, or you are trying to analyze the data sets, two or three data sets, where you know that the mean and standard deviations of the data sets are different. So then how to compare these data values? Then you should normalize those data values. by using this, the observation minus mean by standard deviation. It's a simple Z-score, or you can use a mean max normalization, which is within A and B. The value minus the original minimum divided by the original maximum minus original minimum, and it is scaled down to B minus A. So that is that part you can do. And a generalized transformation is the box-box transformation. That also you can do. Now this transformation usually help you in stabilizing the variability also. For better comparison, you may need to have, you may need to normalize the data, and you may need to reduce the variability. You may need to make the data set normal. It was not very normal. It was maybe it was skewed, and because of the skewness, you are not allowed to use those techniques which are applicable for the normal setup. So in that case, your data transformation can help. And if you are not using the right data transformation, then you are in trouble. So, but this data transformation will help you to make data set normal, where you can apply some nice techniques. It can help you to stabilize the variability. It can help you also to make data sets comparable between groups. So now, suppose you have a skewed unimodal data, then x to the power q type of transformation can be used. The x square transformation makes the negatively skewed distribution more symmetric. And cubic transformation reduce the extreme negatively skewed distribution to a relatively more symmetric distribution. So x to the power of q transformation can be used if you have a skewed distribution, negatively skewed distribution. Now, square root transformation can be used, or log x transformation can be used if you have positive skewness, right? If you have positive skewness, then you can use square root transformation or log transformation for transforming the data to make positive skew, to transform positive skew to normal. At least the degree of skewness will be a little bit less, and you can apply some techniques which are good for normal distribution. Okay. So these are there are different data transformation tools that you must know. Here are some others also. Okay. It is possible that not by doing right transformation may overcorrect the shape of the distribution. That is also again a problem. When we apply a cubic transformation to moderately negatively skewed data, it becomes a positively skewed data. So heavily skewed, negatively skewed, we can use a cubic transformation. But if for the moderately negatively skewed data, we apply cubic transformation, it can transform to a positively skewed data. So that has to be also looked into. So right transformation you have to adopt. And before before starting your analysis, that means before processing your data preparation also, take care of this: value mapping or coding and discretization. Now, value mapping and coding, as you know, that for some categorical data, if you want to make some kind of analysis, we use the category, we use the numbers instead of the category. So that is called value mapping or coding. For example, suppose if the subjects, if the units are male or female, we can write 1 and 0, 1 identifying male and 0 identifying the female, or high or the response of a patient in a therapy recorded as low, medium, and high. We can replace that low, medium, high as 0, 1, 2. These are the codes. So this coding, sometimes the coding also helps us to analyze the data. And discretization, you know that where sometimes for the purpose of analysis, you need to put a continuous data in a bin, which you can call as a discrete thing. For example, in case of age, which is a continuous thing, we can discretize it by saying age at last birthday, age according to the last birthday. So it becomes discrete. So you can work on that. So it depends, everything depends on your objective, what is your purpose, and how far approximation you are allowed to do. Okay, so here is another example where there is a problem in conclusion. So critical study is needed. And the problem is not by combining the tables, not that kind of problem which I discussed. This is a different kind of problem. Let us see what is happening here. Now, an example was, study was done where the individuals of same physique who perform a particular type of physical exercise were observed on two variables. One is the time spent per hour on exercise and the calorie intake. So these two variables are recorded, calorie intake and the time spent on physical exercise. Remember, the condition is that the individuals under study, they are of the same physique. Their body structures are more or less same. Okay. Now these variables were recorded for 2 weeks, and the average time spent on exercise and the average calorie intake for each individual were reported. So this was the individual and then time and the calorie intake. So we find out that, so in order to see if higher time spent on exercise correspond to higher intake of calories, that was the objective of the study. So we want to study whether higher exercise, more amount of exercise requires more burning of calories, more intake, higher intake of calories, more need of calories. Now a correlation study was done, a simple correlation. You see, I have not gone to any higher order statistics. Simple correlation study. Now the correlation sum comes out to be very negligible, almost zero, which is not very realistic. What happened here? Now we find that we concentrated on individuals second and eighth individual, which are not conforming to the rest of the data. You see here, individual 2 spends less time on exercise, but his calorie intake was very high. You see here in the data, less time spent, but calorie intake is 35. And more time, and the individual 8, more time intake, more time spent in exercise, but calorie intake is less, right? So this 0.835 and 2.215, this we noticed in the data set. Now, we eliminate those data points. And when we eliminate those data points, then the correlation comes out to be 0.9. So here the actual correlation was masked due to the presence of those two irregular data points. And this is, we call this as the masking of correlation. And this masking of correlation, why it happened? It happened due to those data points, those bad data points. And you can term them as outliers if according to your criteria, if it comes under the outlier region, then you can term them as outliers. But basically, these are the data points, we can say bad data points, which are which are creating the problem, which are not leading us to the right direction, leading us to the right conclusion. So not always you have to use your logic also when you are not getting your good feeling after conclusion, after concluding the data. If you are not having a good feeling, go back to your data and see it and critically analyze all the data points. What is happening? And you can find something wrong there and you eliminate those things and you can get good better description, better conclusion. Okay, so these are the things. And there is something about cluster analysis, but I should stop here now. I would invite questions and then I will answer the questions.
Please, sir. Please, sir.
Yes.
Nitin? Dr. Nitin, are you there? Dr. Nitin? Sir, thank you for a wonderful presentation. In fact, you have very steadily presented all the things actually that is required by from a student point of view as a faculty point of view, because especially I'm talking about transformation. It is a wonderful presentation because I have never seen such a different kind of, except this box Cox. Cubic transformation is again there, and so many transformation I have seen first time. So really it is a wonderful presentation from even my side too. So thanks a lot, sir, for your valuable time. Sir, as a token and vote of thanks, we are presenting some certificate to you, sir. So my humble request, so please stop your screen sharing, sir. Sir?
Yes.
Sir, some query is there, sir. Just once this certificate is over, then I will show you, sir.
Mm-hmm. Sure.
I think, sir, some technical problem is there in sharing this my screen. So your screen is still sharing, sir? You have stopped your screen, sir?
No, I have stopped.
Okay, wait a minute, sir. Sir, can you see my screen, sir?
Yes, yes, yes.
Sir, as a vote token, as vote of thanks, as a vote of love, sir. Sir, as a, this is a virtual gathering, so we are not, in fact, welcome you as a bouquet of flower. So as a, so this certificate, once it is signed, is emailed to you, sir. Please, sir.
Okay.
Once again, thank you and for your valuable time, sir. Thank you, sir.
Thank you very much.
Now I request Dr. Chatrola, sir, is there, sir?
Yes, yes, I am here.
Okay, sir, before proceeding ahead, sir, I request you to present, sir, executive summary.
Okay, okay. Thank
Please.
you. I am presenting.
Please, sir.
Okay, so respected available on my screen, I am seeing Dr. KG Patel is there and other participants. Our first speaker was Dr. Dhanda Pani, principal scientist at NAM Hyderabad. He has given talk on methodological issues in agricultural research. Am I audible to everyone?
Yes, sir. Yes, sir.
Yes, yes. So in his talk, he has explained many things, but some of the important things, we are taking decision based on level of significance. But nowadays there is opinion that scientific conclusions and business policies should not be based on only p-values. Proper inference is required for full reporting with transparency. He has also explained only non-significant results can explain different 4 types of things. There may be poorly designed experiment or poor choice of treatment or poor data collection strategy, or there may be really no difference among treatments. He has also emphasized use of ANCOVA by taking some covariate and generally plant population in field experiments. He has also emphasized optimum plot size by explaining Fairfield-Smith law. He has also given weightage to incomplete block design, where within block comes more than 20 or 30 treatment at that time go for incomplete block design. He has also with examples shown some softwares are not giving proper result for not all value, but say some specific value. So before using softwares, be cautious. He has also said we are using CD, means critical difference test or least significant difference in many ANOVAs, but where there are more than 6 treatment, please try to use some other test like Tuckett test. He has also taken one more example where we are doing mistake in analysis for field experiments, or where observation we are recording over different periods, say days after 15 days, 30 days, 45 days, like that. At that time, instead of taking period as a factor, he has advised to consider it as a repeated measurement ANOVA. So he has explained very well. Other second speaker was Professor Srivastava from MS University, Vadodara, Gujarat. He has elaborated errors in choosing appropriate statistical techniques and some remedial measures. He was, and everyone we are knowing that data cannot speak itself. We have to use proper statistical tools, and in framing an experiment, he has explained 6 phases steps in detail, like from starting to deciding objective to drawing the inference. He has also explained for different scales. Scale means how we are measuring data, nominal, ordinal, interval scale, and ratio scale, which different statistical tool can be applied. He also explained in depth correlation and regression study, and particularly logistic regression. He has explained in very much depth. And for that, he has explained some different tests. Our third energetic speaker was Dr. Arpan Bhaumik, scientist from IASRI. He has delivered talk on some anomalies in design of experiment during field experiments. And particularly he dealt with analysis of variance based on field data experiment, where assumptions required for this are violating. And for this violation, he has explained additivity by taking some illustrative numerical examples. And in depth, he has explained logarithmic, square roots, arc sine, and Box-Cox transformation. Our fourth speaker, Dr. Dijesh Mishra, scientist from Center for Agricultural Bioinformatics at IASRI, New Delhi. He has taken topics from plant breeding side, genomic selection, and diagnostic measures, a statistical perspective. He has explained, because we are a heterogeneous group, he had tried to explain conventional approach and what are the limitations in that by regular or traditional crossing and selection method. Then after emerged marker assisted breeding. Hello. Okay, then after he has explained marker assisted breeding, its advantages and limitations. And due to its limitations, one scientist named Mu Weisson has given genomic selection procedure. And again in genomic selection procedure, people have started using linear model, but with linear model, there were some challenges were there. So recently, Raja Ratnam named statisticians has proposed one method based on these lasso tactics, and using that different method, this team has developed different softwares, and they are available on for public use on the webs. So these four speakers were yesterday. Now today's in morning session, Dr. Subhas Kumar Yadav has delivered talk on common errors and their diagnostic and its solution in regression analysis. So starting from basic thing, assumptions required for regression model, he has started, and in depth he has explained 3 assumptions which are very much faced by the researcher: heteroscedasticity, multicollinearity, and autocorrelation. How to find out these 3 things and how to overcome these 3 situations, that he has explained, and sometimes with example also he has tried to explain this thing in regression analysis. In morning, another speaker was Dr. Kingsley, scientist from Institute of Agriculture, Economics and Policy Research, ICAR. He has delivered talk on common errors in application of econometrics and linear programming, a partial alternative. The topic was very much new to many of the audience, and the topic was related to econometric modeling. He has started from very simple things, like simple thing means initial things, sample size, then a preliminary data analysis, how to fit regression equation, and how to improve those model. And in improving those model, different stepwise procedure he has elaborated. He has also elaborated 2 terms, spurious regression and endogeneity biases. Now in today's afternoon session, Dr. Sudhir Srivastava from Center for Agricultural Bioinformatics, ISRI, has explained his talk on analysis of proteomics data in regions, heterogeneity in spatial reference to missing value. Now, protein and peptides are produced in living organism. They are not constant. They are continuously changing. And how to analyze this data where missing data is also occurring, say up to 50% of the data are missing sometimes. Also some machine related errors, means instrument related error is also there. So to overcome all these things, he has explained different steps with software available on the internet for free use like DanteR, MSS Stats, PandaView, Panda, MSQRock. But particularly in his doctoral thesis, he has developed one software, SATP, Statistical Analysis Tool for Proteomics. And this software he has developed in R, which is free language. And at present, this software is available. Its web address he has provided to the audience. And last speaker, due to only session is of 2 days, Dr. Bhattacharya. He is Dean of School of Sciences, Vishwabharati University at Shantiniketan. He has taken topic right statistical technique for right situation test of significance. He has started and teach the things in a very elaborate way. Those who are not having even simple statistical knowledge, that can be understood from his speech. And everything he has explained, say cleaning of data or how to detect outlier by taking real example, by say it is a correlation study or this way. So his 8th speaker has given great pen to make aware about the recent things in our statistics. So thank you very much, patient listening to me. Okay, thank you. Yes, Dr. Alok ji.
Thank you, Dr. Thank you, Shatrala sir, for briefing all the lectures in innovative way. In fact, all the important points that you highlighted as delivered by different speaker or expert of their field in last 2 days. Thank you and thanks a lot, sir.
Thank you, sir.
Before proceeding ahead, I would like to request our dynamic, visionary, and energetic person and the personality behind this webinar, Dr. KG Patel, sir, Dean Faculty of Agriculture, Campus Bharuch, to say few words in this occasion as a blessing, sir.
Good evening, all of you.
Thank you, sir.
Dr. Alok, I am audible?
Yes, sir. You are audible, sir.
So again, good evening to all of you, particularly Dr. Alok. He is a webinar coordinator. Dr. Khatrola, now he's given a remark on this webinar of today's. Different participants from various corners of the country, students, faculty members, and from various stakeholders, all the participants. So today's webinar, now it is going to end. Diagnostics and Remedial Measures for Common Error in Application of Statistics. So actually this 2-day deliberation from various speakers are very truthful. Dr. Khatrola elaborated detail regarding the talk given by various speakers. Total in 2-day deliberation, there are 8 speakers. They elaborated at length regarding the problems and how to overcome that problem in the statistical analysis. Particularly the first speaker, Dr. Dandapani from Hyderabad. So he has given a very nice talk on critical errors and how it can be overcome, and which are the mistakes in the analysis. So particularly in the periodical observation, that the scientist can sometimes do mistake regarding periodical observation, and that can be very difficult to analyze the data. So how that problem can be overcome, that's he elaborated very well. The second speaker also, Professor Rakesh Srivastava from the MS University. He has also elaborated the errors in choosing appropriate statistical technique. So the proper statistical technique can be utilized to analyze the data with different tools. He also delivered talk regarding scaling data and how the correlation regression can be done. So proper conclusion can be had. Sometimes we have sufficient data, but if we will not have proper analysis, then we cannot come to the right conclusion. So he also given a very nice talk regarding the errors in choosing appropriate data. Now the third speaker was Dr. Arpan Bhumik. He also discussed nicely some anomalies in design of experiment during field experiment. So here we are having two types of experiment in the laboratory and field also. So field experiment, particularly, it can be used by the agriculture scientists more and more. So yeah, so how he want to number of treatments are varied. So the different subjects are there: plant protection, genetics and plant breeding, some agronomy, soil science like that. So which design can be properly utilized for that? That is very important thing, because after all we have to come to the conclusion for the use of the society. So designing the experiment is very important thing. So here discussed very nicely, and that can be very useful to the students and faculty members while formulating the design. So the number 4 speaker, Dijesh Chandra Mishra, he has also discussed diagnostic methods in genomic selection. So I think these topics will be very useful for the genetics and plant breeding and those who are working in the varietal development. Particularly, they discuss regarding the conventional methods and how it can be vary with the our marker assist genome reading systems. So that is very, but there are some limitations also there. So he also discussed some limitations. So this will be useful very well to the students and faculty members also. Our the Dr. Subhash Kumar Yadav, he also discussed rightly regarding the common errors and their diagnostic and its solution in regression analysis. So unfortunately, they are doing some mistakes while handling the experiment. So, and that can be comes in form of the errors. So how the errors can be overcome while analyzing the data, that is very important things for the right conclusion. Also, Dr. Skingley from the ICR, he also discussed regarding the common error in application of the econometric and linear programming partial alternative. So this is very important because some common errors, these are also very useful our research worker. Our the other speaker, Dr. Sudhir Srivastava, he also discussed regarding the analysis of proteomic data in presence heterogeneity in special reference to missing value. Okay, this is very important thing because as and when we do the experiment in the field conditions, sometimes we can some plots can be missed because some there are number of the factors are affecting while handling the experiment. So this is missing plot technique is very important to analyze data and for the right conclusion. Our today's last speaker was Professor Bhattacharya, Dean and Professor Head at Vishabharati University, Kolkata. He also discussed regarding critical analysis of data to take right decision. So data are there, but number of things are required to analyze it because the correlations or regression like that, but transformation is very important thing. Data are there, it's very 0 to 100. So which transformation can be useful for the analysis data because sometimes data are there, but we cannot come to right conclusion, and that cannot be utilized for the common public. So right decision is necessary to analyze the data, and right conclusion also necessary to interpret the data. So we can get very critical treatments for the of the society. So all these speakers are very important. They are very learned scientists, and Dr. Alok Srivastava is, I think, success to coordinate with all the peoples to give the success of the seminar. I think after the 2-day deliberation, all the participants are I think, well satisfied because statistics is very important subject. Suppose the scientists are doing the work, but without a proper interpretation, then we cannot come to the good conclusion. So this webinar, I think, very useful for the future strategy of the for the scientists to conduct the experiment, to find out the proper design and how interpret and conclusion. So this webinar will be very useful for our research worker. So again, I congratulate Dr. Alok Srivastava and his team to organize this today webinar. And again, I congratulate all the teams of the College of Agriculture Bharuch for the successful handling this webinar. So again, I wish and good luck to all of you. Thank you.
Thank you, sir, for kind blessing words and highlighted all the important points given by the different speakers. Thank you, sir. Now time come to hear the person under his leadership. University research reaches to the highest peak, and university bagged so many awards in sense of release variety and many more. So with all honor and regard, I would like to call and request Dr. S.R. Chaudhary, sir, Director of Research, Navsari Agriculture University, for his blessing word. Over to Dr. Chaudhary, sir. Please, sir.
Hello, namaskar to all of you.
Namaskar.
So, Dr. K.G. Patel and entire team for organizing a very, very meaningful webinar, and topic is really very, very useful to statistician across the country, and indirectly you will be contributing to the research of your institute or university. The topic diagnostics and remedial measures for the common error in application of the statistics. It is very, very relevant, and whoever has decided this topic, let me congratulate him, because it is a very, very meaningful topic, Dr. Srivastava and entire team. And I know the research without the statistics is meaningless. And for making any conclusion or drawing any conclusion, statistics play a very important role. And if you see the statistics itself, it is a very, very difficult subject as far as my subject is concerned. I am a surgeon, and it is very difficult for me to understand the statistics. So there are the many disciplines which usually keep away from the statistics, but you are the part and parcel of the statistics, and you contribute the research in many fields. You support the research in agricultural field, you support research in horticulture field, you also support the research in animal husbandry and any other wings of research. So this is one thing. So let me first thank Dr. Alok Srivastava, Dr. K.G. Patel and entire team for giving me an opportunity to connect with you. As I can see at present there are 64 participants there, and it is known that the participants across the country participated in this webinar. So it is a proud moment for the NAU Navsari, and this particularly the College of Agriculture Bharuch. It is not a very old college, it is a new college, but the college is doing very well as far as the various webinar of the various subjects they have been organizing over the last couple of months, and this is one of the series of the webinar they have been organizing. All the faculty members of the College of the Agriculture Bharuch, they are very much trained, and they are now used to conduct any program on the as a webinar. And as I told last time, Dr. Srivastava and entire team, please listen. Now you have organized so many webinars. Now I expect a little bit more. And one 3 days national seminar has also been approved by the authorities of our university, and you will be organizing in next month. It's okay. But now you are competent enough to organize any training program, and particularly in the field of the statistics, which is a much more neglected or underprivileged field. If you consider the rest of the subject of our agriculture and allied sciences, statistics is not paid much importance, or as far as the faculty, number of the faculty members are concerned, they are always overburdened. There are very less number of the statisticians in the university, and but still all the faculty members, if you see the committee member, it may be the PG committee member of the student, you need one statistician. Whenever we organize the Agresco, where the research outcome of whole the year is reviewed, again the statistician play an important role. So the role of the statistician is you cannot is a much important. The role of the statistician is much important. They play a very, very vital role, an integral part of the research. So I have a lot of respect for the statistician, and therefore I request Dr. Srivastava, Dr. Pandya, and others, because you are competent enough to organize 7 days or 11 days, 10 days, 11 days this training program. It will help your faculty, and if for that, if you need any kind of the support, we will be with you. And thank you for giving me an opportunity. I was busy with some other work, so I cannot say much about the statistics, but whatever you have done, you have invited faculty for lectures across the country. So from the Directorate of Research, I personally thank all the speakers who have contributed for making this webinar successful. And on the at the same time, also thank all the participants for joining the hands with NAU Navsari. And I hope that as and when NAU again gives a call for participation, probably all the participants will be readily accept our invitation, and you will be with the team of the NAU Navsari. With these words, thank you very much, and once again, congratulations for organizing such a successful webinar and on important topic. Thank you, Dr. Srivastava, and thank you all of you. Thank you very much.
Thank you, sir. Thank you, sir, for recognizing our work and as well as giving due importance to our work, sir. In fact, we as a personally on behalf, first time I in fact hear this kind of words. So first, again, thanks a lot, sir. And as per your expectation, we will try to definitely going to propose. In fact, very dynamic team is there. Dr. Garde is there. Dr. Nitin is there. Dr. Arvind is there. No doubt, under leadership of Chatrola sir and Pandya sir, definitely we will going to propose one program, sir, as per your expectation.
Thank you.
Thank you, sir. And now coming to the next session, I would like to request Arvind, Dr. Arvind, to give a vote of thanks. Over to Arvind.
Thank you, Srivastava sir and dear sir. Good evening, everyone. It's my privilege to have been asked to propose a vote of thanks on this occasion of today's webinar on diagnostic and remedial measure for common errors in application of statistics. I, Arvind Chaudhary, on behalf of Department of Agriculture Statistics and entire supporting team of Navsari Agriculture University, let me extend a very hearty vote of thanks to our Chief Patron and Honorable Vice Chancellor of Navsari Agriculture University, Dr. Z.P. Patel sir, for your unconditional support and motivation. I would like to thank our Patron and Director of Research, Navsari Agriculture University, respected Dr. S.R. Chaudhary sir, for your timely and valuable guidance. I may like to express our sincere thanks to our President and Dean, Faculty of Agriculture of Navsari Agriculture University, Dr. K.G. Patel sir, for your support and encouragement for organize such a national level event in this pandemic situation. Dr. K.G. Patel sir is always motivating us to conduct such an event in a different way and on different topic. So bottom of my heart, thanks a lot, sir, as you are available both of the day and spare your valuable time in spite of your busy schedule. A big thank you to our convener and registrar and professor and head of Department of Agriculture Statistics, Dr. H.R. Pandya sir, for your support and coordination. Also, I would like to thank our co-convener, Dr. Alok Srivastava sir and Dr. Yogesh Garde sir, for arranging such a nice webinar and inviting renowned speaker. A big thank you to our coordinator, Dr. H.N. Chatrola sir, for your suggestion and valuable guidance. I may like to express thanks to our organizing secretary, Professor Nitin Varshney, and myself for continuous monitoring and handling of this event. I must mention our deep sense of appreciation and thanks to our invited speaker, Dr. Dandavani sir, Professor Rakesh Srivastava sir, Dr. Arpan Bhovik sir, Dr. Dvijesh Mishra sir, Dr. Subhash Kumar Yadav sir, Dr. Kingsley sir, and Dr. Sudhir Srivastava sir, and Dr. Bhattacharya sir for sharing your finding and informative lectures in easy and understandable language. with us and who made this webinar very interesting and a grand success. We are all inspired by your great words. Ladies and gentlemen, once again, I want to state that we are all most grateful to Higher Authority of Navsari Agricultural University and IT Cell Department for providing smooth IT service in this event. Last but not least, I would like to thank all the participants who take part and make it a grand success. We thank you for being with us this evening. It has been a great pleasure for us. Thank you very much. Jai Hind.
So thank you, Dr. Arvind. With the permission of chair and dignitaries, I would like to conclude this program with your permission. Thank you, sir.
Yes, thank you to everybody.
Thank you, sir. Thank you, sir. Sir, one announcement is there related to certificates. All the participants are humble requested. Please be with us as per day 100 certificate option is there. 100 certificates will be delivered in per day. So once you fill your feedback form, accordingly you will get. So within 8 days you will get the certificate. Okay. Once again, thank you. Thank you.